science, oui. À mon avis, ça va jamais marcher.
Son pas venir avec là.
Ah, il y a le filtre aussi.
Yeah. And a very important one. So if you put like that, everybody looks bad.
Il n'y a pas de scotch.
Scotch,
Tape.
cellophane. It doesn't stick well.
Yeah. No, this I understand.
We need a specific,
Yeah.
so we have to.
Ah non, non, je vais keep
So we start.
oh, go ahead.
You need microphone?
Ah, je m'en fous plutôt que directly.
No. If you need a microphone, here is this one here. Press it. It's continuous. Okay. So good morning, everyone, to the LIX colloquium of 2014, theme on data science. We are happy to have Frank Packard, who is the Director of Research and Education in Polytechnique, and he will give us a welcome. Frank.
Thank you. I would like to welcome, I think it's a, I'm talking loud enough. I would like to welcome you here. It is a pleasure to have you on campus, and I'm glad that you have found your way because it's not easy. From time to time, we lose some people trying to get here, and as you can see, the campus is changing very quickly for those who don't come here every day, and there is a saying in French that when construction is going well, everything goes well. So I'm very glad to introduce this LIX colloquium on data science. I'm not an expert on data science because I'm a mathematician, so I understand absolutely nothing about data science, except that I pushed the teams to launch some programs in data science, and I have to talk about data science pretending I understand it very, very well. So I would be very pleased. I would have been very pleased to attend the whole colloquium. And usually people in my position, they have an excuse that they say that they have to go to a meeting and things like this. But here I don't have any excuse because I realized that I can, during my meeting, I can watch the conference on YouTube. And so usually people do many things on during meetings. So it will probably be the opportunity for me to learn more about data science. And so I think that in SACLE also there will be a lot of people. The data science will become very important because there are a lot of institutions of SACLE which are involved in the data science in different forms. And so as we can see also by in the speakers list. And so definitely in the future, I think that SACLE will become one of the important centers in data science. And so we will see. And I wish you a very happy and successful colloquium. Okay, thank you.
Thank you. So thank you very much, Frank.
So what do I have to log on the YouTube?
You will go. So this is for everyone. So if you want to see the event by video streaming, you just go to the page of the colloquium, which is this one. And there you have a link that sends you to YouTube, and you can see the event live. Of course, on the consent of the speakers that they are fine to be streamed. Okay. So thank you very much. And now it is time for Olivier Bournez, the director of the Laboratory of Informatics of École Polytechnique, to give us a short introduction and give us a few words on what is LIX, what are the purposes of LIX, etc.
Okay, so welcome in LIX. So I will have a few slides. Just actually, the purpose of this slide is to welcome you and say a few words about LIX and LIX colloquium. So this is a LIX colloquium. Okay, so I'm Olivier Bournez. I'm the director of LIX. LIX is the computer science lab of École Polytechnique. So I guess that here you have to understand that X means École Polytechnique, in case you don't know, if you want to survive in this place. So LIX is here in this building, Alan Turing building, shared with Inria also. So LIX is about 130 people from CNRS, Inria, and École Polytechnique. So people here, there are about 40 permanent researchers or professors. We are organizing three main teams, three main axes about algorithms, combinatorics, modeling, secure and mobile computing, and symbolic computation and proofs. Each axis is made of research teams, so I will show in only one slide our teams and research teams. So this is a lab supported by CNRS, École Polytechnique, and also INRIA. We have common teams with INRIA. We have a range of industrial collaboration, so I just gave names of people who collaborate with in the last 5 years. And we also are strongly involved in teaching or education, and not only in research here. So we also have several shares, like a new one, for example, with Cisco launched this year. So in one slide, LIX is made of 11 teams. I try to put some keywords here. And there are teams like Models and Systems that contain several groups. So for example, the group of Michalis Pazirzianis about data science that we want to develop. And I propose to talk with you if you want to know more about other teams. Michalis will say a few words about what is done in this group. And I just want to tell you now what the LIX colloquium is and what is the purpose of this colloquium. So basically, the idea is that every year, mostly in fall, we organize a colloquium in the lab. So the themes of this colloquium change from year to year. The idea is mostly to give and to focus on the team we want to develop and we want to point out as a new team. So this is exactly what we are doing here with data science. So you see that the teams can change from year to year. And so I just want to say that you are welcome to this data science LIX colloquium, and welcome to LIX and LIX colloquium.
Thank you. Okay, now it is my turn to offer a small introduction to the colloquium, some background. Let's hope that the equipment will not betray us. Fine. So, so this is the introduction to the LIX colloquium on the theme of data science. I just wanted to, let's say, give a small introduction. There is this Gartner hype cycle. So Gartner is a consultant firm in the United States that studies the evolution of various technologies and products, and they have this kind of cycle where a technology or a product has an increased expectation, then it goes through some bad period, and then it comes to probably maturity and productivity. And as you will see here, there are a lot of technologies that have been, let's say, hyped for some time, and now they are in the productivity area. So you see that big data and data science are in the top of hype. So this means that there's a lot of expectation, but probably there are several risks. My personal opinion is that probably we are a bit further than that, because there is already productivity with big data. The biggest industries in web search, for instance, they have been using big data technologies since several years ago. So in any case, big data is a topic that has been quite, let's say, demanded in the last several years. It has been even in the press. So you see in New York Times articles about big data. In Le Monde, which is the main French newspaper, there are articles how important are the data now and in the future. There is even hints for the future that the education on data science will be an interesting issue. And in this context, there is this new term that was coined recently in an experts group of ORCIN. This is called datacy, and it is coming from the emerging data analysis literacy. And the idea is that we educate the society, the citizen, in a manner that he or she understands the basic concepts and is aware of the consequences. In this case, data science and big data analytics, they can and they should be offered as a service, available to citizens, to industries, to the governments. And there are few ideas on deployment, such as smart cities, developing countries, official statistics that are aware of the big data that flux the society and the industry. And of course, Polytechnique has responded to the challenge about big data in the sense of starting a new academic master that was launched already this year. It is a joint effort with other prestigious French universities. And also there is a professional training for people already in their careers that want to, let's say, update their skills. So we have launched this program and it is running, and we think it will be quite successful. And then I would like to give you a very, very brief introduction to the topics that we deal with in our team, which is called data science and mining in the context of LIX. So our primary research area is graph mining and social networks, where we deal with community detection, and we deal with new metrics for evaluating communities and clusters. And this can be used as well in the area of spreading and epidemics, which is interesting in the case of social networking, with interesting applications like churn prediction, privacy-preserving knowledge extraction from data, and also from biological networks. There is a prototype that you can visit where we present on a per-user basis the best communities with regards to authorship and citations as well. We are also in the area of web and text mining, where we deal with topics of time-aware information retrieval, and specifically for novelty detection when we have text or new streams. Then we have come up with a high risk but very interesting, in my opinion, topic, which is graph of word, which is an approach that I would say challenges the traditional bag of word approach and considers documents as graphs with interesting applications in summarization, keyword extraction, etc. And we do applications on news recommendations, on event detection in news streams, in web advertising and automated snippet generation. And we offer prototypes. This Match the News is a news recommender that is it is a plugin approved by Firefox. And last but not least, we are interested in machine learning in the context of big data. So we have done work on distributed spectral decompositions like spectral clustering. And we have an ample experience on real-world projects in those areas. There's no time to elaborate on that. But the interesting thing is that I would like to to acknowledge several people for today's event and also for the help and support that I had so far in my launch in LIX. So I would like to thank the sponsors like LIX for organizing and hosting and supporting financially this event. The Center for Data Science, which is a new organization at the Saclay level that promotes the topic and the objectives of computer science, of data science. I would like to thank very much Evelyn Reisak, who has been the soul of organizing this event from the administrative point of view. Also my colleagues and students, Frangiskos Maliaros, Maria Rossi, Kostas Kianis, that they have devoted so much time and effort to make this happen. And I would like to thank the INRIA personnel for their help during these preparations. And last but not least, I would like to thank Jean-Marc Steyart, he's here, I think, for his support all these years, for his friendship, and for the strong, let's say, relationship that we have developed. And I wish the best for his retirement. Okay, so after that, let's go to the program of the colloquium. So the program, we have managed to organize, thanks to the efforts of Kostas Skianis mainly, a live streaming of the event. So people that are not here, or if they wish to view the event and the talks after as well, there is a YouTube channel that we have organized, and the event can be seen there, can be watched there. So the program consists of a set of talks. You see here the invited speakers. So we will start with a keynote speech by Santo Fortunato, professor in Aalto University. Santo is well known for his seminal contributions in the area of graph mining. And this choice was mainly to stress the fact that data science and big data is an interdisciplinary topic where different disciplines and sciences meet and contribute for innovation. So Santo is coming mainly from the area of physics, and there is a very nice amalgamation of efforts. I mean, we have also started to publish in physics journals, and it is very interesting that very interesting papers, especially in graph mining, appear in journals and conferences outside computer science. So this is a message that we have to go interdisciplinary in the future. Then we have Gregory Greffenstedt from INRIA Saclay that will give us an interesting talk on focusing on the aspects of big data involving text and information retrieval. Then we will have Eric Dossier from the University of Joseph Fourier from Grenoble, that he will give us some new insights in the area of classification in web-scale taxonomies. Then we have Manuel Gomez Rodriguez from Max Planck Institute. He will give us a talk on the incentives of users and how this shapes social activity in social networks. Marc Tomasi, a researcher from INRIA Lille, that he will talk to us on machine learning topics for graphs. And then we will have the lunch break. As you see, there is a kind of grouping of the talks. So we have the academic talks just before lunch. Then after the lunch, we will move to slightly different topics. So we have Balázs Kegl, the director of the Center for Data Science. He will give us a talk on his experiences from the challenge that they have organized in Kaggle about the Higgs. This is This is a topic coming from physics, lots of data from experiments, and how do we deal with prediction of interesting events. Then we have Peter Triantafylou, professor from the University of Glasgow, that will talk about big data and big systems. Peter has long experience in the systems of data management, so he will give us insight at this level. Then Themis Palpanas, professor in Paris Descartes. There we will have an introduction and insights on big sequence management. Sequential data are very important. We will have a coffee break, and then there will be the industrial part of the colloquium. We have 3 invited speakers from the industry. So we have Richard Washington from Google. He will give us a talk on the understanding process of videos on YouTube at large scale. Stefan Hadinger from Amazon Web Services. Stéphane Guinet from AXA. AXA is very much interested in the value of big data in the industrial sector, which is the insurance sector. And if we are still fit enough, we will spend a few minutes on closing the event and probably concluding with interesting topics. So, thank you very much for being here. I invite Santo.
Thanks.
So as Santo is preparing his computer, I would like to introduce him. So he's a professor of the Complex Systems Department in, a professor in the area of Complex Systems at the Department of Biomedical Engineering and Computational Science in Aalto University in Finland. Before that, he was the director of Sociophysics Laboratory at the Institute of Scientific Interchange in Turin. Santo acquired his PhD in theoretical particle physics in the University of Bielefeld in Germany. And then he shifted into the area of complex systems. And currently he's interested in areas of network science, especially community detection with graphs. He has published numerous papers in prestigious journals like Nature, NAS, Physical Review Letters. He has been cited excessively and
never excessive. never too much. You know?
Never enough. So we are very happy that he's here and he will give us his latest insights in the area of communities. So,
thanks a lot, Michaelis. Thanks, everybody. I've been to Paris many times. It's the first time that I'm at the famous École Polytechnique. And one of those boxes you want to check before it's too late. So I'm happy that I could make that. And this sounds like a very interesting event. And Michaelis is right. I mean, this endeavor, data science, network science, is becoming increasingly interdisciplinary. Perhaps it should be organized better in the sense that, you know, there are still too many communities really going their own way and without realizing how many other interesting insights can come from other areas. So, and it's a pity because sometimes you do something, then you realize somebody did the same thing, or somehow it could have been interesting to talk to this other person in order to improve at the end the outcome, what you did to get further insight. I'm a physicist for training, although I hardly define myself a physicist today. I've seen something about the Higgs bosons here. I was a theoretical particle physicist, and until 10 years ago, in fact. And then I decided somehow to make this big turn. I was already old when I did it. I was an advanced postdoc, and I moved to Indiana to work with Alessandro Lespignani, which is when I started doing these things. And when my first result on community detection of some, oh, sorry, yeah, yes, I don't know. Yeah, okay, perhaps I can keep it this way. All right, so, and today I will just expose some of the main things we've been doing in this area recently, so in the last few years, and also because I don't know, I'm not sure how many of you are familiar with that, so it's going to be some sort of introduction to the field and motivation. Peter before said to me, who's interested in community detection today? That's of course an interesting question. And the answer is simple, everyone, which is the reason why, you know, as long as this is the, of course then we can elaborate if this is the right thing or not. We can also, you know, this is more philosophical, and I'm open to remarks in this direction. But it's really true. I mean, as long as there will be networks around, there will be people looking for clusters in networks for a number of reasons. So it's an ill-defined problem, which has of course drawbacks. It has also the advantage that everybody thinks to have a solution for it, because since there is no, there are no real benchmarks, there is no clear-cut path to validate things, then any approach is as good as any other. That's a bad start. But the good thing is that I mean, we really collected a lot of insight, a lot of contributions from many different communities, and many people with many different, very different expertise. A lot of good stuff that's difficult to catch up with. We're doing our best. So let's see where we are. These are the people who were involved in my research in this area over the last 10 years, say. And I would like to emphasize particularly the work of my former PhD student, Andrea Cicchinetti, who is now at the University of Umeå in Sweden, who is behind a lot of the stuff I'm going to tell you. And he's also managed to become, through the things, one of the best-known names in this area. And then more recently, another PhD student, Darko Ritz, and postdoc Richard Dust were involved in most recent investigation that I won't have time to get to, because it's kind of still preliminary, still needs to be verified. And then a number of other people. You may know some of these people. So this is the way I would like to structure this presentation. There's going to be an introduction about what the problem is, why we think it is interesting, because so many people think it is interesting. Then I will get into the perennial debate or whether you can solve the problem, you can get interesting solution to the problem by using a global optimization approach or a local optimization approach. And I'll tell you what I mean by that, because I know that for people working in optimization, this expression has a different meaning. So I'll try to tell you exactly what it is. And so about local approaches, I will discuss a little bit our contribution in this direction, which is this method called Oslo. I'll show you also the website and everything. And then I will spend some time in discussing what is, my opinion, the most important thing in this area, how to test a method, how to say whether your new contribution is really adding something to the field. Because, of course, especially when you have an ill-defined problem, it's too easy to say that, you just take a couple of data sets that you like, you find a great performance there, and that's the end of it. Life is not too easy, so we should really focus, in fact, mostly on validation procedures before even thinking of developing algorithms to solve the problem. And then I will summarize. So let me take this very schematic example here. It's a network with 15 nodes. You can see these three colors. You can see that it is a connected graph, so there is a path between any two nodes. And there are three groups identified by the colors that have this peculiar feature, which is apparent, and it's not so easy to make quantitative, although in this case it's kind of, it's not difficult either, that have a high density of links inside and a comparatively lower density of links between them. So the green edges here will represent the bridges between the communities or modules or clusters. I may be using these words in the same meaning during the presentation. And the colors indicate the members of the same group. So given that we are methodologists mostly, so we don't really focus too much on the specific class of systems that we like to investigate, and that's a mistake, because in my opinion, the future of this field is towards domain-dependent application, which could also make the problem a little less ill-defined than it is. But so far, until today, and for the next few years, people will still approach this problem from the generalist point of view. So thinking about something at the purely topological level, something that in principle works everywhere. And these are mostly the methods that I'll be discussing today, although then I will say something about what in my opinion should be done in the future. We're already doing that, in fact. So thinking about all possible application domains, you can think that communities are groups of people with common interests, and that's why they interact more frequently with each other, or scholars working on the same field. They can cite each other more frequently than they cite other scholars, so they get to work with each other more frequently than they work with other scholars. Proteins with equal or similar functions, so this would be the biological domain. Papers on the same related topics, and so on. You can make plenty of examples. And what's the reason to study this, if there is some? So there are theoretical reasons. Finding the modules is also a way to see how a system is organized internally. study organs, like identifying the liver, the heart, the kidneys of the human body. It's a way to extract, hopefully, features from the nodes which are not apparent, or that you don't have in the when you receive the data set, because you may assume that nodes are in the same classes because they have similar properties. So you find the classes, you can infer the properties. In fact, we are trying to study this aspect, which is again underestimated in this area. It's taken for granted, and that's a mistake because it's not so obvious as it looks. Then there is a thing of node classification. I mean, if you know the modular structure, community structure of a system like this, based on what the clusters are, you can identify nodes which are somehow heavily embedded in the clusters, like these three, for instance, which do not even share any edge with the rest of the system, from these other nodes, which instead have a function of some sort of intermediate, so gatekeepers between parts of the network. And this is related to what Michele said before. Knowing this, for instance, is good because you can identify influential spreaders of information or epidemics. So this is an important reason why I want to do that. Which has nothing to do with content, just with position, with the possibility of having some dynamics running on it and using the edges to transmit signals, say. Related to that, there is a problem of the missing links. You may know that, of course, there are big problems with sampling, especially when you have large data sets. And that, especially in biology, there is a lot of noise in the associations between, for instance, proteins, genes, whatever network you're going to put together. So because of this noise, sometimes you may have in the system nodes which do not appear to be significantly attached to each other, so they are disconnected, whereas perhaps they are connected, but you just are incapable to notice that from your experiment, from your exploratory technique that puts the thing together. So the missing link problem is a classical problem of social network analysis, been addressed in statistics in many different areas. So there is a huge literature on that, more recently stochastic models. Using clustering could also help a little bit to define a little bit the context, because if you know where the clusters are, you may assume that the missing links are more frequently inside the clusters than between the clusters. You wouldn't solve the problem, but it can give you useful indications. Then there could be also practical reasons. You can make recommenders, for instance, if you have a clustering technique of some use. People are doing that, they're thinking of doing that. So suppose that you have a set of people, customers buying products in Amazon. In a structure like this, you can see that there is a big density of links. Of course, this is a schematic example. So suppose that this is a cluster, then, of customers and products which are frequently purchased by the same people. And then you can assume that because of this guy here is more interesting to buy a ham than to buy a laptop or a book. So it's the same thing. It's a problem of missing link. So if there is a missing link or a link that could be there in the future spontaneously, and of course you don't want it to appear spontaneously because then you lose money. So if you think that there could be this possibility, then you say, oh, why don't you buy this? And that could be a way, to increase your revenues. And another way, it's related to this issue of identifying node features. So in this case, for instance, unknown protein functions. Suppose that it is a protein interaction network. In many cases, even today, despite the big progress in bioinformatics, in medicine, in biology, there are still many proteins who do not have a defined function, or about which there could be doubts, if it's really it's involved in the process or not. So if you have the modular structure of a protein interaction network, then, and for instance, you know that many proteins in the same clusters have pretty much the same function, in this case cytokinesis, you may assume that that's a function of the protein that you cannot really identify. Even if it's not true, that at least it can, can guide a little bit your experiments. It can make you save time and money. Okay, so that's an introduction. I hope that at least shows why so many people are working on this from many different angles. Then, of course, everybody's favorite tool. Then there is a lot of debate about the tools. We'll discuss about this. It is a difficult problem because, first of all, it's an ill-defined problem. But just to tell you what that means, somehow thinking about the example I gave you of these 15 nodes organized in 3 groups, this is the adjacency matrix of this network. So you have 15 times 15. The ones indicate the link between the nodes with the corresponding labels. And the empty spaces indicate the absence of links. If I give you a matrix like this, even if it's small, of course, the eye is a very powerful investigation tool, perhaps the most powerful we have. There doesn't seem to be anything really organized in here. However, if I rearrange the labels of the nodes by putting first the nodes of one color and then the nodes of the other color and so on, of course, which in this case I know, because of course I designed this example by hand, you see that you can transform the matrix into some approximate block diagonal structure, which shows you that there are clusters. Because these guys here have a lot of links with each other, and the same for the blue ones and the same for the yellow ones. I think that I may need bigger. This is almost, the battery is almost over. The signal comes and goes. Yeah. Then I don't know if it's so easy to this. Okay, sorry about that. Yeah. Okay. Oh yeah, it's great. Very good. Thanks. So basically, the whole thing would be to make this transformation in some way and to go from here to here. So of course, in this case, it's very simple because the example is simple. It's a very small system. But doing it, for instance, for Facebook, like a 1.2 billion times 1.2 billion matrix, speaking about big data, poses at least a problem of computational efficiency of this. Not to speak about how good a job it is at the end. It's going to be. So it is a difficult problem. Most important is a nil-defined problem. Like all clustering problems, right? Data clustering and so on. And the most important questions are, what is a community or a partition of the networking communities? And what is a good community? And what is a good partition of the networking? So these are the questions that lead to the confusion, and which lead to a higher confusion, a bigger confusion if you consider further complications that you may have in your data set. For instance, the data set can be a directed network in which the edges have a direction. So going from A to B is not the same thing as going from B to A. Like the web, for instance. The web graph is a directed graph. Hyperlinks taking you from A to B, but usually there is no hyperlink taking you back. It's only 10–15% of cases. Then, of course, the links can be weighted. They may not have all the same importance because you can have information about how important, how heavy the interaction is between two nodes, and you don't want to waste this information because it's useful information. So they wouldn't be all equivalent. There are links which are more important than others. You want to take this into account. Then there is a problem of overlapping communities, which is exemplified in this very schematic example, in which you see 3 clusters, and these purple nodes are shared between 2 clusters. Thinking about the examples coming from social networks, you may convince yourself easily that usually people belong to multiple circles at the same time. Family, work colleagues, football buddies, bowling buddies, everything. These are different groups, but it's the same individual belonging at the same time to multiple groups. This is called soft clustering. And of course, you can imagine that it increases enormously the number of possible solutions of the problem, because then you have all these degrees of freedom that you have to take into account with respect to hard partitioning. Finally, you also have hierarchical structure. So complex systems are usually hierarchically organized. Thinking about, for instance, the human body, there are the cells, they form tissues, they form the organs, they form the human body. All these are equally relevant levels of organization of the system, in this case, the human body. You cannot say that the cells are more important than the tissues, they are more important than the organs. So, and this is shown by this example here, which is, of course, again, very schematic, of a system which has 2 levels of organization, 16 groups of 32 nodes each, which are together in 4 macro groups of 128 nodes each. So a good method shouldn't make a difference between the 16 and the 4. It should be able to tell you that there are 2 levels of organization. A level with 16, micro level, and a level with 4 macro groups. But there's another complication. By far today, the largest class, the most popular class of methods designed to solve this problem is what I still call global optimization. At least I try to specify what it is in order not to offend anybody, in case there is an expert on optimization in the audience. So by that I mean that there is a function of the partition, so it's not a function of the cluster. So you give a score to each partition. The score is called Q, and each partition gets a score. And the best partition of the network is the partition with the highest score. It's usually upper bounded, so there is a higher upper limit, and therefore you know that you're going to have a partition of these features. It will be trivial, of course. But of course, in general, you expect to find a measure which is sufficiently sophisticated that it doesn't give you trivial results. So what is the problem when you use an approach like that? Whatever the function is, I'm not to say anything about a particular function, an approach like that. The problem is that the answer depends on the whole graph, because you're giving an estimate and a judgment on the whole partition of the networking communities. So the answer changes if you consider only parts of it. Let me give you an example. Suppose that this is a network that I put together, this gray spot. I'm not very good at making visualizations, so perhaps I should get some help from other people in the presentations. And suppose that a method like this gives you a division in 3 clusters, which are the blue balls. Now, but this network that I'm analyzing could easily be a sub-network of a much larger system, which is the other gray ball. If I apply the same method I used for the first partition to the whole system, in general, I would get a different division of the system in the portion that I used to analyze before. That's in general what would happen. So the answer really depends on how big your system is, which is strange because you would assume that communities, especially in a large system, are kind of local structure. As big as they can be, each community should be substantially smaller than the rest of the system, if the system is very large. But that starts to be a little bit more philosophical. I'm telling you what I think. But this is true. So, and of course, people are backed by that as well. Any social network you can put together is a subset of the social network of all people in the world, right? Knowing each other. Whether it's a Facebook subgraph, whether it's anything you can put together, an experiment. So applying your global technique just to the subset will give a different result than if you apply the same technique to the whole thing. And then you see how it divided into classes the portion of the system analyzed before. So that's a serious thing, which has to do with just the approach as a whole. But people are not backed by that, I admit it a bit more than others. In 2004, speaking about global optimization, these 2 papers appeared. These are 2 of the most cited papers in this business, 2 of the most cited papers ever. It's more than 5,000 citations each. They easily go at about 10,000. They're very simple, beautiful papers. And in these 2 papers, in this paper first, which appeared a couple of months before the other, Newman and Girvan introduced the gold standard, what used to be the gold standard of the field, and the most representative global community, global quality function for community detection, which is called modularity, the modularity of Newman and Girvan, which is like E equal to MC squared for this field, just to give you a reference. So there is an equal, there is the M, there is the C, there is a square. So what is this? So Q is how we indicate modularity. M is the number of links of the system, or the network, total number of links. So it's not the mass. And C is not the speed of light. C is just an index here to indicate the cluster. And C is the number of clusters. So each cluster gives you a score. And then you sum over all the clusters and divide by N. For each cluster, you compute this difference. LC is the number of links inside the cluster, connecting nodes of the same cluster. DC is the total degree of nodes of cluster C. So it's the sum of the number of neighbors of nodes of cluster C. Number of neighbors which can be both inside and outside of the cluster. Because if they were only inside, DC would be just twice the number of links. It's not so simple, otherwise we get a trivial result. M is again the number of links. So I remember I was just starting to work on this because I was curious about the famous Gilman-Newman method, which was introduced 2 years before, and this is just a follow-up of this. The measure was introduced to select the results of a hierarchical divisive method introduced by the same 2 authors 2 years before, which is actually what opened this field to physicists, to many other communities, because I didn't know anything about it until that day, like many others. And any hierarchical method gives you, again, a hierarchy of partitions. If you have n nodes, it gives you n minus 1 partition. So if you have 1 million nodes, it gives you basically 1 million partitions. And then the question is, which one shall I pick? Of course, it's a big progress compared to trillions of partitions you can have if you have no clue about how to divide a cluster and the system in clusters. But it's still, we're still kind of miles away from the solution. If you have 1 million partitions, which according to your method are totally equivalent, because there is no way to discriminate. That's the reason why they introduced this measure. So let's compute this measure for all the partitions of the method, and let's pick the one with the highest value. But since McNewman is one of the smartest guys in this business, he immediately thought that perhaps he didn't really need to make this combined approach that was presented here. That modularity could stand by itself as a new method to find communities in ground. Because if we believe that the partition is the better, the higher the value of Q, then let's just optimize Q. So we don't need any preliminary step. And that's what was done in this paper, which appeared just a couple of months after that. The guy is a quick thinker, and opened the age of modularity optimization. It was 10 years ago, in fact. Where the goal is to find the maximum value of this measure over the set of all possible partitions of the system. You know that there is going to be a non-trivial partition doing that because the measure is bounded. It cannot be bigger than 1 on any partition you can make on any system. So there's going to be an answer to that. And since that day, there have been really, literally, thousands of people just doing this. The problem is that, of course, like most interesting problems in optimization, it is an NP-complete problem. It was proven almost right after that, 2007, by Ulrich Brandes and co-workers. So that's the reason why people could propose a wide variety of heuristics to try to approximate the solution in the quickest and most efficient way. That's what generated most of the papers you still see today. So when I entered this game in 2005, when I moved to Indiana, modularity was becoming rapidly the method to solve the problem, not only in physics, because you already know there are so many papers from computer scientists from any subset about this. So, and mathematicians, I mean, everybody's really was curious to do something about it. It's a very simple object, full of properties that when it was introduced, nobody had a clue about, because now we know these things much better. And to be honest, I didn't really help the popularity of this method, because the first result I made when I was there, together with Marc Barthélemy, who was at the time visiting the lab, was showing that the method has a fundamental problem, which is now called the resolution limit of modularity. So this is the same expression you've seen before. I just rewrite in a different way. There was dc squared divided 4m squared. I just consider it this way. I like to write it this way because this shows you, perhaps in a more manifest way, that there is a fundamental scale hidden in the measure. Because it is as if you were measuring dc, which is the total number of neighbors of the nodes of cluster C, as in units of square root of m, which is the total number of edges of the system. Okay, it's fine. That's a remark. That's the way I present this now, because the original approach was a little bit more naive. What kind of implication does this have? I call this a modularity scale. I mean, if the system is very large and m is millions, billions of edges, square root of m can be a very large number. Still 10,000, 100,000, depends. Especially when you speak about big data, large network datasets which are available today. So, what are the consequences of this? This is the diagram that now has become quite popular, and people try to crack this as a pathological example. The yellow circle, the green circles, represent complete graphs with p nodes. So it's a set of p nodes who are fully connected to each other. I should get a better picture for this. so that I don't need to tell you. Which are usually indicated in graph theory as KP. Complete graphs with P nodes. So they're all identical, and they are weakly connected to each other by just a single link. So this guy has two neighbors, so there is one node of this guy is connected to one node of these other guys in this symmetric ring-line structure. Now, if I tell you, or at least already, even if you didn't hear about the subject before, based on what my introduction is, this system should have an intuitive community structure, which is the set of the cliques. These are also called cliques in social network analysis. So it's complete graphs. So each clique would be a community, because of course they are the most compact object you can imagine, because all the links are inside, and outside they have the weakest possible connection to the rest of the system. A single link cannot be, otherwise it will be disconnected, but the system must be connected. So that's an intuitive thing. However, because of this scale, depending on how many links there are inside each, basically how DC compares with square root of m, if DC is of the order of square root of m, or smaller, then for modularity it would be beneficial to create clusters which are given by the combination of neighboring cliques to give you a higher value. Now, I'm not talking about a specific heuristic to optimize modularity. I'm talking about the measure as a whole. So if somebody gives you that you have some sort of God-given procedure to find the exact maximum every time in an infinitesimal amount of time, then you will have this problem. So of course, any heuristic will have the same problem too. So it's a problem of the measure, not of the specific way you maximize the measure. Okay, this is a question. Then I say, who cares? I mean, you will never see an example like this, right? This is a toy model. Yes, but what you should be worried about is that if I give you a network that you've never seen before, and if you apply modularity optimization, suppose even if you can find the absolute maximum of the measure on this network, and there is a cluster of the partition that you found in which DC is smaller than the square root of m, then you cannot tell a priori whether this subgraph looks like this, so it's a compact object, indeed a cluster, or like this, it's a combination of clusters, because in both cases, modularity will put everything together. You cannot resolve structures smaller than that. So starting from this paper, then people start, try to see if there are ways to go around it. And the easiest thing they could think of at the beginning, which for a while it seemed like it could solve the problem, was just introducing a resolution parameter inside the definition of modularity. That would be gamma. This is the same definition you've seen before, but now there is a gamma, tunable parameter. When gamma is equal to 1, you recover the original definition. However, recently, with Andrea and Cicchinetto, one of our latest papers on that, we showed that even if you have a resolution parameter, the only thing you're doing, you're just shifting the preferred scale of the method. But if you have a system in which you have clusters distributed wildly in scale, and usually real systems have this kind of distribution, they don't have a preferential scale, except in some specific example, then even if you have a situation like this, you run into double trouble, because you won't still be able to see the smaller ones if the reference scale, once you fix gamma, is larger than that. But at the same time, you will break, so larger clusters which are much larger, so portion of the network which are much larger than the scale that you fix by fixing k, a gamma, they will be broken into pieces. Just because the system, the method tried to create a situation in which this scale is the dominant one. It's just a bias of the method. So I should be careful also with multi-resolution methods. And I think that now we convince people that indeed this is probably not a good way to go. So we couldn't find values, so the resolution parameter eliminated both problems in artificial benchmarks in which you have broad distributions of scale for the clusters, like our benchmark that I'm going to introduce next. Now, so global optimization probably is not really the best thing you can do for the reason I told you. There's a theoretical reason that it depends on the specific part of the system, because the answer depends on the whole system. And because, in my opinion, communities are local structures, especially if the system is very large. So it would be better, in my opinion at least, this is really philosophical now, to make a local exploration of the network. So if you have to go for an optimization process, you better optimize a function of the cluster instead of a function of the partition. And that's the reason why in the last years also local methods, local optimization approaches have become popular as well. So modularity is still very popular. And then I'm going to tell you, a specific framework that we designed for that. The advantages are communities are local, in my opinion, but that's more philosophical. Then there is an absence of global scales because you just try to optimize something in the area where you want to put things together. So you don't care about the rest of the system, just make a local explorations. There shouldn't be any resolution problems. And there is also computational advantage. You can just analyze parts of the system. For instance, the system is too large that you cannot possibly complete the simulation, the analysis in a realistic time, or by the time your PhD student ends his studies. Should be bad, because then you will have just one paper or less. Then you can do a local exploration. At least you can cover or try to clusterize part of the system. Maybe the part you're most interested in, around some specific nodes that are, for any reason, interesting to you. Okay, so the implementation is pretty much the same. You have now a new quality function, which is a function of the cluster and not anymore of the partition as a whole. And you look for a local maximum or minimum, but usually it's a maximum of this measure. One way to do it is according to the local fitness method we introduced some years ago, in which the quality function is pretty much related to a fitness of the cluster C. Cluster C would be whatever is here, all the green nodes inside this contour. K in C is the number, is the degree, the internal degree of this cluster. Yeah, I'm sorry. But I don't want to overlap too much with that, otherwise I will have the screen. And so it's basically the number of links you see here times 2 inside. And then there is K out, which is the number of these red dotted lines, the number of links connecting the cluster to the rest of the system. So of course, if you have a good cluster, you should have a K in, which is comparatively larger than K out. That's intuitive. So the larger value, the more compact the object is, the better separated it's from the rest. And then we also put the resolution parameter here. So the idea is that you start from a node, anything, you look for its neighbors, and you include the neighbors which gives you a higher value of the fitness, and you kick out the nodes which gives you a lower value of the fitness. And you repeat the procedure until you find a situation in which no addition of a new node or no removal of a node which is already in can give you a higher value of FC. That's the whole thing. And this diagram was just supposed to show you how things work in practice. Oops, why does this? So you start with a node, check the neighbors. So the red one become nodes of the cluster. And the advantage of this procedure is that you then repeat the procedure starting from a node outside that is not yet assigned to a cluster, but you can invade nodes which are already been assigned to clusters. In this way, you recover overlaps between the clusters. So you don't put barriers, say, okay, I cannot invade this territory because this node is already labeled. And in an example like this, these nodes which are intermediate, like this, what is 28, 20, 25, are shared between clusters, and they will be assigned to both. They will get both labels. But of course, you can choose your own fitness function. It's really your choice. The approach will work just the same way. Sorry about that. Okay, more recently, we have specialized this by introducing a more refined fitness function which computes the statistical significance of a cluster, which is basically what is the probability that a cluster is generated by random fluctuations. You can elaborate more if you're interested offline. I just advertised this because it was the first multifunctional method which could account for edge direction, edge weights, overlapping clusters, the same way you've seen before, because when you make local exploration, you can naturally invade areas which are already covered, so you can assign multiple labels to the same node, and hierarchical structure. So I said to Andrea, look, we're not going to publish a method because I personally don't like to develop methods because I'm more interested in the concepts. even if the problem is defined, just because of this, if you want. So I'm not letting you publish this unless you solve all these things, because most of the methods are not easily extendable to these cases. They not give you the hierarchy, for instance. They do not account for overlaps. They don't work, especially when the edges are directed. So this method really covers everything. And if you're interested, you can play with it. This is the website. You can find the code. It's in C++. You can compare it and play with it. So if you find anything interesting, let me know. If you find the flaw, don't let me know, because I want to be depressed. Okay, so the last thing I wanted to tell you is about, my opinion, it should have been the first thing instead. So maybe in the future I will start with this, but you know, it's difficult to, because I have to speak about methods then, so it's better to give a clue about what the methods are before talking on how to validate them. So that's the reason of this choice. How to test a clustering algorithm? Nobody knows, to be honest. There is a set of artificial benchmarks in which most people would agree that the clusters of this benchmark should be the clusters that any good method should be able to resolve. Of course, you must have some sort of ground truth, and the system and the method should recover the ground truth better than the best methods nowadays. That's the principle what you should do, what you always do, especially in computer science, but whenever you introduce a method to solve any problem. The most famous class of benchmark graphs with communities inside was introduced by Condon and Karp in 1999. These are two mathematicians. For some reason, this paper was overlooked, and even when Mark Newman and Michel Gibbon introduced their own benchmark, they didn't realize it was just a generalization of this. Maybe it's just didn't know about it, so they don't cite this paper. It can happen. So you have a set of n nodes which are divided in L groups. That's why it's called planted L partition model. And then you have two parameters. There is a probability P that vertices of the same cluster are joined, and a probability Q that vertices of different clusters are joined. And the idea is that if P is bigger than Q, then the groups are communities. Because the probability that nodes of the same color are connected, it would be higher than the probability that nodes of different colors are connected. So it's pretty much the simplest thing you can think of. That explains its popularity. The so-called Gilvan-Newman benchmark is a specific version of this benchmark when you have 4 groups of identical size, and all the nodes have the same degree. But we didn't like that. We didn't think it would really reflect what real networks with communities look like. So more recently, in 2008, we proposed what is now known as the LFR benchmark, of which this is a snapshot for 500 nodes, which is a special case of the planted partition model, but in which we introduce power law distributions of degree and community size. You know that, of course, the distributions of degree, or the number of neighbors of a real network, is usually very heterogeneous. There are the hubs, which have many more links, many more neighbors than most of the other nodes. So we wanted to embed this feature in the system, and we also wanted to have a broad distribution of scales. And you can see here that the classes have different sizes, very large ones and small ones. So this is the paper, and this is where you can find the software that people have been using in these years to create this class, to create these systems and to test their algorithm on them. But of course, we did this because we were curious, once you introduce these complications, which methods that were popular at that time, and some of them which were not popular at that time, that became popular after this, Infomap and the Louvain method, which is probably now the most used method, how well they will perform on that when you introduce these complications, because most of them were doing quite well on the 4 groups test of Newman and Gibbon. So we took 12 methods based on how easy it was to find the code, how kind the developers were to give us the code when it was not openly accessible, and how good we were to write the code ourselves when the method was sufficiently simple to do the job without taking months to do that. So that explains the choice that we made. Here you see the list of the methods. This is the way it will be labeled in the plots you're going to see. And this is the complexity. There are different classes of methods. We really wanted to test as many different approaches as possible. There are divisive methods in which you detach links one after the other until all the nodes are disconnected. And then you go through a whole hierarchy of partitions in between. Like, of course, the most famous Gilvan-Newman method. Then there are modularity optimization methods, which are these 3. So grid optimization, and extensive, exhaustive optimization, simulated annealing, which is parameter dependent. Then there are methods based on random walks, including InfoMap, which is the winner of this, which was the winner of this competition, and then other spin models, expectation optimization, and so on. Anything we could get our hands on. These 12 diagrams show the performance of each of these methods on our benchmark, LFR benchmark. The 4 curves correspond to 2 different sizes for the benchmark, 1,000 and 5,000 nodes, so already much larger than the 128 system that people have been considering until that day. And S and B indicate 2 different ranges for the cluster size. S indicates clusters with minimum 10 nodes, maximum 50 nodes, and B, which is big, indicate a range of 20 to 100 nodes for the cluster. So this is basically the range where the cluster sizes are distributed. We only wanted to see this because we wanted to check how the performance depends on the size of the system and on the distribution of scales. And you see that in some cases there is a dramatic difference. So you can also see that since there are many different scales, because of the resolution limit, exhaustive modularity optimization performs very badly when the system is large and the clusters are small. That would be the green line. So even here, where this mixing parameter μt indicates how separated the clusters are, so μt equal to 0 means that basically they are disconnected. μt equal to 1 means that basically they are all in a big blender. That's the reason why when μt is equal to 0, you would expect to have high performance. This is the normalized mutual information between the detected partition and the planted partition. But for modularity, for instance, you see here that already when μt is very small, when every method should be able to detect the clusters, because of the resolution limit and the fact that here you have a broad distribution of scale, the performance is very bad from scratch.
What's the y-axis?
The normalized mutual information. So it's a measure of similarity of partitions. Of course, you can choose other measures. For some reasons, this became famous because it was used in the previous analysis on the given Newman benchmark. This would be a follow-up of that analysis, even if we were not the original authors of that one. So, you know, it's the usual thing. People start to use a measure, and then if you want to make meaningful comparisons with previous analysis, you must use that thing, whether you like it or not. So that's the reason why we use that one. So NMI, normalized mutual information. And then you see, of course, that the performance will degrade at some point when the system becomes, when the classes become too mixed to be distinguished from each other, and that's inevitable. And the question is, which method decays the latest? And you see that this is what happens for these 3 methods. But this one is particularly slow. These are mostly linear complexity, and that's the reason why today these 2 methods are perhaps the 2 most known methods in this business, right or wrong. I think we contributed to that. Nobody knew that this method, this InfoMap method was so good on that day. Not even his developer, Martin Rosso, is now a good friend of ours, probably because of this. Things had to start from somewhere. And then I also tell you, look, I told you, look, I mean, perhaps you should make it hierarchical. You should allow him to find overlaps, because if he just stays, you know, for hard partitions and so on, not many people are going to use it. And that's what we did. So there are papers after this in which you extended the method to cover these cases as well. Okay, that was pretty much the last thing I wanted to tell you, except for this test that we introduced for the first time in this case, which is, again, in my opinion, one of the most important tests, because it's a negative test. So you give a random graph to a method. If the method is decent, it should tell you, look, there are no classes. Because if you have a random graph, of course, there is the same probability of associating any 2 nodes. People say, okay, but then, I mean, maybe a method can do that, right? It's not obvious, because modularity, for instance, modularity optimization finds also high values, so high modularity partitions also in random graphs. That has been studied extensively, also with some beautiful math using spin glasses, belief propagation, something that seems too complicated for me, just to predict in how many fragments modularity optimization, real modularity optimization, so not any heuristic, would break a random graph. So in this case, we have only 10 examples, because for 2 others, they were too slow to give results in a meaningful time. We were in a hurry to finish the paper. But it's the same set of methods as before, and the 2 curves correspond to 2 different random graphs. The Erdo-Schoeni graph, in which all the nodes are essentially the same degree. That would be ER, so the black spots. And the scale-free graphs, a la Balabasi-Albert, say, in which you have a broad distribution of degrees. And this is as a function of the average degree So what is the average number of neighbors of each node? How many clusters the method finds? So of course, the only acceptable answers are two. Either you find one cluster including everything, or you find n clusters, which are the individual nodes. This is still acceptable, because it means that there is nothing in between. But as you see, that's not what you get all the time. For instance, even Blondel, so the Louvain method and the InfoMap, when the system is not sufficiently dense, so when it's very sparse, there are very few neighbors, it still finds non-trivial associations between the nodes, which is, of course, noise. The MCL, which is, sorry, the CFinder, which is used to be the method that published in Nature by Thomas Wiczek and Gail Palla, Thomas Wiczek, and so on, was the first method to address heavily the issue of overlapping clusters, finds even more than 1,000 clusters here, even if you have only 1,000 nodes. All the networks here have 1,000 nodes because of the overlap. When you have the overlap, of course, you can have many more clusters than nodes. So it's an amplifier. So many people say, how is it possible if all of them have 1,000 nodes that you can get to 1,000 clusters? Because of the overlap. Okay, so anyway, this is a test that I would recommend. Whenever you make a new method, make sure that it doesn't give you, doesn't find signal when there is only noise. So it's a negative test that I strongly encourage to anybody. You can choose different random graphs, but the principle is the same. In a system that is designed not to have any particular association, except for random fluctuations, a method should be able to tell you that this is noise and not a signal. Okay, guys, so that's all. So what is a community? After 1 hour, I tell you I don't know. So perhaps you're disappointed, you wasted just the last 60 minutes or 45 minutes. There is no unique answer. Not only because the problem is ill-defined, but also because, in my opinion, it should be really contextualized in the specific domain that you want to study. You don't want to lose the features of the particular class of systems that you analyze. You want to use them. And if you use them, you can do a better job than any of these generalist methods I told you, or any other you could introduce in the future. Is there a magic method? No, of course, for the same reason. So you should go towards domain-dependent approaches. Global optimization methods have important limits. A conceptual method, that the answer depends on the size of the whole system. So it changes if you consider subsets of it. And in particular, there could be resolution problems, like in the case of modularity optimization. Global optimization looks more natural and promising. That's my opinion. And then, importantly, don't forget this, attention on validation. So, shall we use real clusters with ground truth information? Recently, many people are starting to do that. We are starting to do that as well. There are nice papers by Jürgen Leskovich, Robert Kleinberg, and so on, in which they try to see whether these annotated classes have anything to do with structure. You may know some of them. They're published in KDD and other important conferences, where I usually don't go, but I read those papers. So that's very important. And then, if you're not happy with this introduction, and you want to know more, even if this is now a bit obsolete, because there have been thousands of papers published after that, you may want to take a look at the survey that I wrote a couple of years back, which is the only comprehensive survey on the topic. And then you say, who is gonna, who wants to take clusters in graphs? So you can see that there are apparently many people want to do that. And at least students who want to learn from this, it's kind of a book in a sense, found it very useful. So I hope that you will find it useful as well if you never read it before. The last thing I wanted to tell you is shameless advertisement. We are organizing in Helsinki next year the first global conference in computational social science. So basically studying social dynamics with data-driven approaches. There have been several conferences organized at the community level by specific areas, by social scientists alone, by computer scientists alone, by some physicists alone. We're trying to put everything together. These are the people who are coming to Helsinki next year to this conference. It wasn't easy to get all of them. All of them have confirmed, except David Lazar. But there's an interesting bunch of people from different areas. People who are in Time magazine, top 100 people, most influential people, and so on, or consultants of the World Economic Forum. So there is time until December the 7th to submit an extended abstract of max 2 pages. If you have anything to say about this, there is also a rough list of topics that you may be interested in, and certainly what Michaelis does is relevant. And I'm sure that after today, I will find also other customers for that. If you never heard about this, so I will try to disseminate it widely. So I hope to see as many of you as possible in Helsinki next year. It's going to be fun. It's the first time of this kind, and who knows, maybe there will be a series, maybe not. It gives me enough to do for the time being. Thanks to everyone. Thank you.
So thanks a lot, Santo, for this very interesting.
Well, you know all about it, so maybe.
No, I mean it is always nice to see, and I heard some things that I didn't know already. But I think it was very comprehensive and a nice immersion into what is graph clustering.
It was the idea.
Are there any questions from the audience?
I think Peter, after mentioning you, get to say something.
Actually, I was wondering about the testing. I think this is, I agree with you, this is very important. So isn't there a way that one can artificially create, synthesize a number of graphs with specific clustering properties?
Yes.
And then test all the existing algorithms with respect to both the false positives and false negatives.
Yeah.
Because I think this is what you introduced actually is a way to come up with, well,
False
positives. Yes,
sure.
So has this been done? I mean, it would seem to me that this is what people would be doing.
You know what? I mean, I shouldn't say this for myself, but until our benchmark, people were, I don't know, idle or I don't know, too naive. They were just using the same simplified object over and over. Up to the point, this 4 groups test that you see, up to the point that it was not possible anymore to improve anything, and it was not possible to learn anything from it. So we were the first one really to just look, I mean, you should do this negative test, and so on. After that, there have been some follow-ups. They tried to make our benchmark more realistic, to introduce triangles, for instance, or motifs, which are absent because it's essentially a random graph. It's a random graph. So I can say I'm very happy to hear this because I would be extremely glad to see more of these attempts around. And not because at the end we need an entropy of or a proliferation of different models, and then I say, okay, mine does better in this than in this one. But because it's good to discover the limits of methods, what they can do and what they cannot do. So I think that there is still a lot to do. That's why I always end this kind of general introduction with this encouragement to everybody. So think about validation, especially you computer scientists who know all about it. And now actually the attention is towards ground truth validation from annotation. Just to also to falsify or to verify this thing that I said at the beginning about whether clusters, structural clusters, enable you to detect any feature which is non-topological. But there is still a lot of things, in my opinion, there is still a lot to be done in the validation thing from the artificial purpose. Because at the end, we have to agree on some sort of basic concept. And if you go to the real case, there are so many factors that play a role, it's difficult really to keep track of all of them. So the answer is yes or no. I mean, there is nothing on this. If you have any idea, I would be happy to discuss with you or with anybody, and that's a second lot of info. Thanks.
Any other question from the audience? Well, I have several ones. I think we will go offline at some point, but I would like to, let's say, stimulate probably discussion. As far as I understand, there is this density concept that has been dominating the clustering, especially in the graph cluster domain.
Yes.
Now, in the presence of new kinds of graphs like directed, signed, etc., do you see any different intuitions or any different concepts that can represent the cluster other than density? For instance, we have been dealing with, or we have been studying a little bit clustering at the directed graphs level, and it seems that density is not the only,
sure,
and the semantics are quite different. They are not even well defined. For instance, flow within directed graph cluster could be interesting. So do you have any insights or any?
Yeah, I'm sorry, in the last sentence you said what I was thinking to answer to that. Flow is, of course, perhaps the most studied alternative to density, especially in the case of directed graphs, where you can really make a huge difference. In the original Infomap paper by Rosberg and Beckstrom, this method I thought that didn't give you any details, but the method is based on random walks. Basically, the idea is that you have a guide which can walk freely, following links at random, from one node to the next. If you have a very compartmentalized system, then of course the worker will spend a lot of time in the cluster before leaving. That's been implemented in dozens of different ways, some simple, some very complicated. Infomap does this. But when it was introduced, I mean, of course, it's still somehow related to density, because of course, if you have more bridges inside and less bridges outside, it immediately gives the probability to stay inside and so on. So at the end, but in the case of directed networks, you can make a huge difference. So you can have something which is very sparse, in which anyway, for just the way the links are conceived in terms of direction, the guy can stay trapped there for a long time. And they gave a couple of very nice situations, very simplified toy models, toy graphs, in which they really show what, for instance, a modularity optimization approach, a density-based approach would find versus what informatic would find. Just also to say, look, we're not looking necessarily at the same type of thing. They are coincident, maybe in the case of lack of direction, but it could be very different in the case of presence of direction. So I would invest something more about flow, but to be honest, as you said, this would be also very, very nice thing for further investigation, because people are too concerned about high density, high separation. Classes today are this, even today, despite this thing.
Especially with these annotated data sets by Leskovec, etc. I think we have to, if we, let's say, agree that this is ground truth and we have to adhere to that, then we need to probably discover new kind of measures, new kind of...
We're doing this right now.
Yeah. Okay, great.
It's of course kind of interesting to do. But let me tell you, when I said at the beginning, I have physics background and so on. This first paper we made on this structure, on these annotated classes that I didn't present, I usually give a couple of slides, gives a provocative message. It shows basically there is some sort of gap between these annotated classes and the structured classes you can find. And the reason is probably, as you say, that there are two reasons. Either there is really very little to do, that these features have not anything to do with the linking probability of the nodes, and that's of course not a nice message. Or we are not really going after the right topological characterization of the classes. And this is the other thing we would like to verify, because at least in this case it's possible by making experiment testing different variables to see if there are signatures, topological signatures that are common across different classes of annotation. It looks very simple, but you can imagine how many problems we had to publish this first message about this in the physics community, because they give to the concept of ground truth a much deeper meaning. You're just reading, but we have to change the word ground truth in the title. So just to tell you this, right? Because otherwise the guy will not say, no, this is not. Who tells you that the links come from the annotation? Nobody. That's what I want to find out. That would be the more computer science approach. But it's difficult when you speak different languages. That even if I can understand because I come from that community. So this is the future. Yeah. So any of course idea would be most welcome in this direction.
So thank you very much again.
Thanks, guys.
And let's welcome our next speaker.
Yes. This is the
So
one.
our next speaker is Gregory Greffenstedt, who is a senior researcher, scientist at INRIA Saclay. Here we are collocated. Before that, he was a senior manager of Exalit, that used to be and still is the French search engine. Senior scientist at CEA, which is the French Institute for Atomic Energy. A principal scientist at Xerox Research Center in Europe. He holds more than 20 US patents, and his main interest is in natural language processing and information retrieval. He has acquired his PhD from the University of Pittsburgh after a bachelor's degree on mathematical sciences in Stanford University. And as I mentioned before, his main topic is natural language and information retrieval. Thank you very much, Gregory.
Thank you.
Here.
Hi, I'm going to be talking to you about text and big data. Recently, if you go to any European Commission meetings, you find them using more and more in respect to data science this acronym called GAFA. Yes, hold on that. GAFA stands for Google, Amazon, Facebook, and Google, Amazon, Facebook, and Apple. And those 4 companies are reasons why it's difficult to find postdocs these days, because they're hiring everything that comes out of the academic systems that has any knowledge in machine learning. Google and Facebook are interested in selling, all 4 companies are interested in selling things. Google and Facebook sell publicities. Amazon and Apple sell products. And they're all interested in what we saw in Santos talk about, finding communities of people. So they know who to give the publicity to or who to pitch a product to. So a lot of the big data you find has to deal with links between people and links between products. And a lot of it has to do with numerical data too. And that looks good. And so a lot of the numerical data that's in big data has to do with now that machines are producing their own data. For example, cars are producing tremendous amount of data about their own performances, and companies want to be able to use that to predict how cars work. Text is a slightly different beast than numerical data and than graphs. So I'm going to give you some of the characteristics of text and how it fits into big data. Here's an example from yesterday, the day before, of text and big data. There was recently this report in England about finding blame for an attack on a policeman by some terrorist in England last year. And they found that this terrorist, or this crazy person, had put up on his website threats of attacking people a long time. And this minister was complaining that Facebook hadn't noticed that and hadn't warned the ministry. And so this is one example. If you can actually treat a lot of big data, maybe you can find things like this. This minister is unaware that Facebook doesn't filter out things beforehand because actually he doesn't know what the data is, how big the data is, and how impossible it is to filter out every possible threat. Last week in the French newspaper, we had the same type of article. There was called Jihad 2.0, the fact that social networks are being used to recruit a lot of the terrorists in France and in other European countries. And here we learn what you might already know, that Twitter and Facebook do not practice any active surveillance on what goes on the websites because it's impossible for the moment. So one practical use of text and big data would be to find threats, and that's what a lot of the national security agencies are hoping to do. And in America, they're gathering all the data that you can possibly emit to find terrorist threats. And more peaceful application is to find out the voice of the customer. So here's an example also from this week. This is a very hot topic. That Sony, constructor of electronics, has 650 million interactions with customers in a year, often through call centers, through emails, through posts on social networks. And they like to find out what customers feel about a certain product. So this means analyzing the textual information in those call centers and in the post and trying to extract whether they're positive or negative, if you're positive or negative about some product or some aspect of a product. Okay, thanks. So these are two examples of trying to use text for some purpose, either for security or for sales. If you've been in any big data talk, you've seen these big data talk about using these 5 V's as a mnemonic for what big data is. And I'll show how text fits into these 5 V's. The first one is volume. So here's an example of some of the volume that text produces. In Twitter, there are 58 million posts per day. And this is a graphic of the posts from 2007. Up until now, we can see that it's growing exponentially. There is an estimate there's 300 billion emails sent per day in the United States. So multiply that by a factor 5 or 10 to get the number sent in the world. And that gives you an idea of some of the volume. For web pages, another big source of text, the Internet Archive houses about 400 billion web pages. In an index, like in Google's index, there's estimates that Google indexes 50 billion web pages in its index. I worked at Exolib up until last year, and Exolib index is 16 billion web pages. On the other hand, Google has said that it has seen 1,000 billion, 1 trillion URLs already. That was in 2008. So the number of web pages that are actually indexed is very small compared to the number of web pages that are out there. Facebook has 4-5 billion new pieces of information shared every day from its users. And Reddit has a common website for recycling text and images of cats. Has 41 million posts, and then there's 400 million comments on that post every year. So this is a lot of data. So this is the idea of the volume. So obviously text falls into the first three. As for velocity, we also have the same problems as in velocity. There are 4 million Google queries per second. So if you want to test what's going on in the world, you have to be able to treat 4 million queries per second. Now Google actually has enough power to do that because they respond to each question. There are 17 new web pages produced every second, and 50 million new sites every year. And even a website that isn't made for text, for example, Instagram, where people post images, there are 1,000 new comments every second on Instagram. Yelp is a site where people produce reviews, like TripAdvisor. It's very popular in the US, not so much in Europe. Has 26,000 new reviews per minute. Even if we consider old text, like books published, there are still 6,000 books published every year. So those also have to be treated. I'm sorry, 6,000 new books published per day. There's a wiki page that tells you how many books are published per country per year, but it turns out to 6,000 per day. And then in Twitter, you have an average of 6,000 tweets per second, but there are sometimes peaks of 150,000 during things like soccer matches and other events like that. So you have to be able to deal with this text very quickly. And text, as we'll see a little bit later, is harder to deal with than just numbers because you have to transform it in order to extract anything meaningful. Okay, for variety, text comes in a variety of forms. It's not just simple words. There are SMS with all the different special language that linguists are slow in being able to follow or to treat, although a lot of work has been done over the past 6 or 7 years. So that's SMS, which also contains a lot of non-grammatical forms and a lot of errors. Twitter includes other things such as mentions and hashtags, which also have different meanings, and there's sort of the textual things that have to be treated with textual processing. Emails are text usually, but emails also contain other emails. So often you find a link of references to a lot of other emails, and this is a big problem in the domain of e-discovery, and discovering when somebody said something about something else, because emails are actually very complex objects to deal with. There are news stories and web pages, which have a variety of structures because they include images and references and ads. And then there are even books on the internet, but a lot of books contain information that's produced by OCR, which contain a lot of errors. So there's a lot of variety of text. It's not just simple text, as you might imagine. There's a lot of work in natural language processing for dealing with each one of these problems. And in addition to this variety of forms, there's a variety of languages. There are 100 languages on the web out of the 6,000 languages thought to be spoken in the world. Only 100 appear on the web, or a few hundred. And so we have differences of languages, we have differences in form, grammaticality, and so all this adds to just a variety of dealing with it. And then there's a basic problem in language in which one word can mean many different things, or many different words can be used to describe the same thing. So this is all the problems that you're faced with when you're dealing with, which you don't really have when you're dealing with numerical problems. When you're reading the weather or the element of friction on the brake pedal, those are numbers which have one meaning. Text has a lot of different meanings, and it's very ugly to deal with. Okay, another one of the V's is veracity, how reliable an information is. So Facebook estimates that about 10% of its accounts are fake. So that's between 70 and 140 million accounts, which are fake accounts. Facebook would tell you those are fake because sometimes people have 2 accounts and they don't use the other one. But actually, you can go and buy accounts. You can go and buy your own accounts on Facebook. There are a tremendous amount of sites like this where you can buy accounts for 35 cents for an account if you buy less than 100. If you buy 100 to 1,000, 33 cents, and buy more than 1,000, it's going to cost you 30 cents an account. And you can buy them in France, in the US, in Russia, or in Europe. So you can buy your own people on the accounts. So that if you're pumping something from Facebook in order to gather information, you have to realize that information also contains sort of spam. And talking about spam, it's considered that half of the email that's being produced is spam, more than half. This is a percentage of spam that Kaspersky measures, and it's up into about 70% of email is spam. And then the web also contains a lot of spam. It's considered about 60% of web pages as spam. So a lot of things that Santo was talking about community detection implemented in places like Google and Exolete in order to detect when a spam farm exists. It's just out there to create spam to fool people into thinking that this is a legitimate site. There's lots of pages that look very similar pages, like very simple pages. It has this page here has a calendar, it has archives, and it has pictures and lots of other things. But the only reason this page is constructed is to get people to play some online poker game. And this is what a lot of the web consists of. Now, luckily, sites like Google and Bing and Exolete are trying to eliminate that, so you don't see that much of it. But if you're trying to crawl the web yourself, you run into spam at every other corner. And then about 8% of the Twitter users are also bots, robots that just create Twitters, and they're not real people, they're just programmed to create posts. So this is an element of veracity. It's in the text in the big data that has to be considered. And even if you have a real person, you can have a real person who will be selling his services. There's a site called Fiverr, where for $5, someone will do something like this. They'll present, they'll give you a 5-star rating on some Amazon book, or they'll give you a video testimonial for your product. So next time you look at some product on Amazon and you see there's 4 ratings and 3 are good and 1 is bad, you can also consider that it doesn't cost much for the person making that product to make good ratings. Mm-hmm. So that's a big problem of veracity in big data. Although veracity in big data is often considered, where does this piece of information come from? If it comes from Wikipedia, we can trust it more than if it comes from another site. But we have to consider that anytime you let any system open to the public, there's an adversarial relationship. There's people trying to spam the system. Okay, so those big 4 items, big V's, apply to text also. And what about value? To get value out of text, you have to turn it from unstructured data into structured data, something you can use. Because to have value, you have to say, if this happens, then we can do this. So if these 3 people buy this product, then we can suppose going to buy this other product. This is a basic motor behind sales using big data. And so to transform unstructured text into something structured, we use natural language processing. Natural language processing is a whole field. There are people working in computational linguistics on all these methods. And these are some of the applications of those methods. So there's identifying what language things are, dividing things up into words, normalizing words, doing part of speech tagging to find out what the words, which words are important, and to be able to parse the text, and then to extrapolations between text, and then co-reference detection that has to do with pronouns, and then generating text, for example, translation. And this allows us to do summary and sentiment analysis and all these applications. Currently, one problem is that to perform natural language processing in text, you can treat about 50 megabytes per hour per core of your machine. So if you're dealing with gigabytes of information and you want to do it in real time, that means you need a lot of machines doing that in parallel. Okay, another problem we have in text is most of the resources we have in natural language processing, either resources or programs, exist mainly for English. So English covers about half of what's on the web, and then there's lots of information which is in all the local languages. Recently, there was a European program called MetaNet, which tested how much resources existed for each language in Europe. So it's just considered European languages, 22 or 30 languages of the European Union. And they put things into clusters of whether we had excellent technology and resources for this language, or whether things were very good, or things were good, but there was still some areas that were missing, or whether it was medium, there were some prototypes, or whether they were very low coverage. And there were no languages, including English, in the first cluster. So there's lots of things in English which we can't deal with, and this is what a lot of people do when they do natural language processing. They deal with English because it's the most economically interesting language and for which you have most resources, but there's still things not done. And then once we get to the other clusters, we find a lot of languages in Europe which has no resources and no processing available. And then the main powerhouses in Europe, French, Dutch, German, Italian, and Spanish, have more coverage. But still, there's a lot of work to be done with this. So there's, before everything is available to perform big data analysis on languages other than English, we have a lot of work to do. Okay, now I'll go over the two different ways to produce structure from text in natural language processing. There's two main ways to do it. One is to have some resource which tells you some pattern that you can find in text, and put that pattern into some class. For example, this is a part of something called WordNet, which has a hierarchy of words in English. So it has more general to more specific words. And it has groups of words which are more or less synonyms. So something like this resource will tell you, well, if I find puppy in a text, actually people are talking about dogs. And of course, the computer has to know these are similar. So they need something like a resource that says that puppy is a type of dog. And so WordNet is an example of that. And then there are a number of other efforts that have been done on natural language processing, such as transforming what's in Wikipedia into a DBpedia. Then there's verbs and frame nets. In certain fields like medicine, there's a large resource that allows you to find out what the organization is. But in most fields, other than medicine, there's no structure yet. So there's still a lot of work to be done in structuring how language is used in a field like sports and running. Here's what you can do by transforming text into structured information. So this is a site that was developed called EM News Explorer, developed by a joint research lab funded by the European community that analyzes news every day and extracts from that news people and places and other names. So what the natural language processing involved is finding names of people. So this is done with lists of first names and lists of last names and some other patterns that are used. And it's also done by extracting all the names that are in things like Wikipedia. And then there's other names, which are names of organizations for which you need either lists of companies or lists of organizations. And then there's names of countries also. So these all use resources of this first type of natural language processing. Resources saying this item is of this type. And this allows you to extract structure from a text. And another application of this is shown here in this prototype that was from École that went over blog posts and tried to find out when there were errors, when there were faults in a car. So on this axis we have lists of automobile manufacturers and automobile marks, what's called the brand. And on this thing we have lists of patterns of faults in a car. For example, one is noise. So to create this graph, which shows that a certain car is often mentioned with a certain noise, there was a human effort to find out all the different ways you can describe noise in a text. So this first technique in natural language processing is finding lists of things and finding those items in the text. Now, once you can do that, you can treat a large amount of text and extract when certain problems exist for certain cars. And this is useful for, of course, companies. The second method, and the method why there's CAT, is for people, GAFA, Google, Amazon, Facebook, and Apple are buying everybody in machine learning, is using unstructured, using deep learning to structure text. In this case, what often is used is we take, we reduce, instead of having some human say this word belongs to this item, we use a machine to do it. And this represents, for example, all the words that are found in 500 million pages of the web. And this is all the words, and here's all the pages. And so if you can say that each word appears on a certain page, you can use basic reduction techniques to reduce that to a smaller space and create a dimension. It's called a word embedding, when a space where words are pushed together if they're often in the same document with the other words, same words. So in this case, if you have cancer and tumor, they'll be pushed together because they often appear together in the same document, so they become closer in this space. These techniques that were used a long time ago, they're very popular now in deep learning, which converts a word into a word embedding, which is some vector of numbers. So contrary to the first technique, where a word says, you say this word puppy belongs to dog, you just have puppy and then you have some vector of numbers, which is actually similar to the vector of numbers of dogs by some mathematical technique. And then you use these vectors in a neural net in order to predict something, either the next word that appears or some category that this text appears with. And this uses neural techniques to change the value of this, even changing the value of this original word vector. So this is very common now. It wasn't common 5 years ago in natural language processing, but now I was at a conference last week, and about half of the papers use these neural net techniques to predict and do classification. And Eric, I think, will talk more about it in the next talk. So those are the two main techniques used by natural language processing to extract structure. There's about an 80% prediction rate of using this neural net technique to produce the polarity of one-line criticisms of films. And so this is possible because there are a great number of films that have ratings and one-line blurbs in English, and it's more difficult to do this in Croatian because there isn't that much data. Okay, so here's the current state of natural language processing from textual big data. It's good for entity extraction because there's a great list of people's names and organizations and countries. It's good for news classification, and it's pretty good for sentiment analysis for defining when there's a positive or negative sentiment in a word, in a sentence. It's poor for non-English, and it's still slow. So those are the things that still have to be improved. Okay, now I'm going to talk about what's going to change in the near future. I'm going to talk about personal big data. And personal big data is all the data that a person generates by their own life. Because each of you sends and receives email. A lot of people post to blogs. People use their cell phone all the time to communicate using chat. Everybody searches on a web browser, which means all the text of the pages that you search also characterize yourself. So this is part of the information that you generate every day when you interact with any type of electronic device. You also purchase things, and purchasing creates records of what you purchased, which are described by textual descriptions often. So that's another form of text. Passively, without producing text, you interact with text. If you watch things like Netflix means you're watching a certain film at a certain time. That film is characterized by the summary of that film, which is text also that has to be processed. When you walk around with the cell phone on, your GPS coordinates are being captured. And if that's crossed with yellow page information, then you can have textual information connected with each of the GPS coordinates. And that's all the stuff that you're producing right now. So you're producing a lot of textual information that goes with you, and it's being used by the National Security Agency in the US to detect if you're a terrorist or not. But it's not being used for us for the moment. But in the near future, it will be used for us, mainly because of this new phenomena of quantified self and wearable computing that's coming around. So quantified self and wearable computing are going to generate numerical data, but also a lot of textual data. For example, with Google Glass, you'll be recording the conversation you have every day. You'll be recording everything you read, and that's more textual data. And so we already produce a great amount of textual data ourselves, and soon we'll be producing transcribed speech, optical character recognition of every book and article we read, and mapping our GPS coordinates to yellow page entities. So this is all textual information that we'll have to keep and have to process for ourselves. There's a new book called Life Logging Personal Big Data, and they estimate that people hear about 100,000 words, or exposed to 100,000 words either by hearing or reading every day. And so this generates 250 megabytes that is just you yourself gather with your own information every year. And then there's a lot of other information that you gather, including where you were and who you interact with. So this second part of personal big data is what actually I'm dealing with now in India. And if you're interested in this, I'll talk to you later after the pause. And so that's it for the my overview of what text and big data has in common.
Thank you. So are there any questions for Gregory on this topic?
Well, you can't. Unfortunately, when you get into huge volume, it's hard to create an evaluation and to be able to test it. So sometimes people just do it and look at it and do random sampling to find out if that's what they like. Just by hand or other real techniques. If you consider something like Google never really tested its search engine, didn't participate in the Trek conferences to test whether it was doing better search than other search engines in academia. But they tested by whether people use it. So that's different. And also they have A/B testing of whether people click on. They use click-through rates to test things. So there aren't test beds for testing a lot of the stuff that's being produced by big data, which is another whole other field of research.
Any other question? Well, I have one.
Okay.
Gregory. You have been in the industry for several years, and you have shown us that there is this exponential growth of production of data at the personal, at the industrial, at the governmental level. Do you think that at the resources, let's say, side, can we still cope in the future? Can we produce more computing power, more storage, more electric power to handle all these floods of data?
I think the dichotomy is the one I showed, because there are two different techniques. Can we keep on doing things by hand for natural language processing and keep up? Or do we have to go to a completely automatic deep learning approach? And there are many things that have to be done by hand for natural language processing, so we still need a lot of grunt work to do that for languages which aren't English. But for things like classification, the deep learning approach is that's the bet that Google is making. For example, they're opening up, they have something called DeepMind, which they bought last year, which is a big center for machine learning that they're opening up in London. And I know because my son is going there. And they have 5 stories that they're going to fill up with people working on machine learning for natural language processing. And currently they only have 2 floors filled. So this would be difficult for us in the academic community to keep people from going there.
So I see you are very much concerned about this, let's say, flow of people from the academia to specific industries.
Yes, it's hard to keep people, which is why it's good that we have things like the masters in data science, because we'll be generating more people that are confident in that domain. So hopefully we'll be able to catch up, and we'll have people working on the scientific aspects of it more than the production aspects.
Okay.
So thank you very much.
So if there's no other question, and now let's move to the next speaker, which is Eric Gosquet. So Eric is a professor at the University Joseph Fourier in Grenoble, and the deputy director of the Laboratory of Informatics in Grenoble. Previously, he was in the area. He was the area manager of the Learning and Content Analysis Group at Xerox Research Center in Europe. He has graduated from École Centrale Paris, and he received his PhD from the Southern University of Paris. His research interests are in machine learning for information retrieval, computational linguistics, social network analysis, and we welcome with great joy. Floor is yours, Eric.
Thank you very much.
We have the necessary badge.
Yes. So thank you very much, guys, for this invitation. I'm very happy to be here today. I want to talk about a subject which is related to information access at the big data era, which is classification in web-scale taxonomies. So I will start with some context, and then I will go into more technical details, hopefully not too technical. So the need for classification in big data. So as Gregory mentioned, new data become available in different forms, in text, in images, in videos, and so on and so forth. And to give additional numbers, Greg provided some of them. And there is a need to categorize this data. And when I mean to categorize this data, I mean to annotate and archive it. Categorization is basically the process where you take some documents, some objects, and you put them in predefined boxes. And by doing so, you are adding some values, so some annotation, you enrich this data, and you are also archiving it. And then you have, in a way, a structure, an organization that will help you retrieve and browse this huge amount of data. So what we have seen recently is that there are more and more large category systems. So the category system is basically the set of boxes in which you want to put the objects. And as there are more and more large ones involving several thousands of boxes, there is a need to organize them, to maintain such category systems. And so usually these category systems, they are organized hierarchically. There is a hierarchy structure, usually a tree backbone, that sustains these large category systems. I'm talking about category systems and taxonomies in roughly the same meaning. So this is just an example, which is from Demos, which is the directory Mozilla, an open part of the Open Directory project. And the goal of this project was to develop the repository of the web. And this started in the mid-90s. And now you have several million websites in the English version of these category systems that have been categorized. You have in the range of 1 million categories. And there have been a lot of editors manually retrieving web pages and then putting them, archiving them, categorizing them in this category system. And at the peak, there were around a few 100,000 manual editors. So other examples of such large-scale taxonomies involve Wikipedia, where you have roughly 600,000 categories, which are organized in a graph with a tree backbone. It means that it's mainly a DAG, but the most important structure here is still a tree. You've got the mesh that Greg mentioned, in which you have over 27,000 categories organized in a graph also, with a tree backbone again. And then you've got the IPC, the International Patent Classification, 67 categories, also in a tree, and you also have the a bunch of other such taxonomies. So in some instances, for example, for Demos, I mentioned that there were editors manually categorizing documents. In some other instances, for example, for the mesh, people are trying to categorize, to annotate automatically permanent abstracts with some automatic procedures. And the focus of my talk will be how can we define, or how should we define such automatic procedures in large scale taxonomies. So there have been a certain number of challenges that have been organized to, in a way, assess the state of the art in classification into such web-scale taxonomies. The first one was one we launched in 2009 with some colleagues from NCSR Democritus, and this is called the Large-Scale Hierarchy Context Classification Challenge. The last edition was in 2014. Then more recently, we were involved in a European project called BioAsk, and one of the challenges was to try and assess the state of the art on annotating PubMed abstract, that is medical abstracts, with mesh terms. And there is a very well-known system to do that was developed by the National Library of Medicine, and that was known to be state of the art in a way. And one of the issues of this challenge was that several participants using machine learning techniques similar to the ones I'm going to present were able to defeat this system. And then there have been a similar attempt on the image community. Okay, so what are the approaches that are used for classification in large-scale taxonomies? So first of all, they all try to learn from data. That is, you've got some boxes, some categories with some documents, and this provides you with examples. You've got documents that can be seen as some inputs, categories that can be seen as some outputs. So this is your data that you're observing. And then what you do is you try to run a function in a very broad sense that will be able to take a new document, a new object, and put it in one of the boxes you have, in one of several ones. So all of them, they learn from data from already categorized documents. And then they use the learn system, the learn function, to categorize new documents. And there have been basically three main types of approaches to do that. So let's assume that the basic ingredient for all these methods is that you have a classification technology that can tell you, that can say, for example, here at this node, I can try to differentiate between these two categories. I have a document, I can learn to put it either in books or in music. And I can also have, I can also consider more than two categories. So the first, I would say, natural approach to classifying in web scale taxonomy is to say, let us exploit the hierarchy. We start from the top with a classifier that will differentiate between these two. Then, if we are here, we differentiate between these two, and so on and so forth. And then you recursively apply the classifiers when you want to categorize your documents. Another approach is sort of an extension of this one, where you try and use the complete category, but still focusing on the LIX. In most cases, what you want to do is to put the documents, the objects at the LIX. You can start at some intermediary level, but say in most cases you want to go at the LIX. But I won't delve into such methods because they are not really suitable for large-scale problems. And then the last approach is to say, well, I will simply ignore the hierarchy, just consider the div categories, and then I will try to directly assign a document to these div categories. So this was not the last approach. There is another approach which we call mildly hierarchical, where basically what you are assuming is, okay, this hierarchy, this structure was designed by humans, for browsing purposes, for maintenance purposes, but this hierarchy is not necessarily the best one you can have for categorization purposes. So let's try to simplify it. Let's try to remove some dots. And what people did at first was to remove some layers in a sort of arbitrary way in order to simplify the hierarchy. Okay, so what are the challenges in large-scale classification? Well, first of all, it's not clear at all which strategy is the best one. So if you look at this paper, for example, published in 2005, what they say is that hierarchical classification outperforms flat classification in terms of classification accuracy. They also claim that it outperforms flat classification in terms of training time, which is true, and it's really easy to prove in terms of time complexity. But then, if you look at this paper, published in 2010, they say that flat classification outperforms hierarchical classification on this dataset. And this has also been shown on other datasets. So basically, what you have is that some people believe that flat classification is better, and show that on some datasets, and some other groups of researchers show that hierarchical classification is better, and they show that on some other datasets. So then there is a related question, which is, if hierarchical classification is to be retained, which hierarchy to use? As I said, taxonomies are designed by humans, for humans, not meant really for categorization. So one can try one can wonder whether they should not be adapted in order to suit categorization needs. And basically that's what these people are doing, while they try to automatically build a taxonomy, even though there is an existing one already in this dataset. They try to build a taxonomy in order to achieve fast prediction and have good accuracy. A slightly related point of challenge is the one related to the scale of the datasets. So these are just some numbers taken from the LSHTC campaign. So this is a subset of the DMOS collection, and this are two subsets of the Wiki collection, and this is the International Pattern Classification collection. If you just take DMOS, for example, you've got 16 billion parameters when you are doing a standard machine learning approach, and 500 billion parameters for Wikipedia. So in terms of disk space, just to store the model for classification, you have 100 gigabytes in the case of DMOS and 2 terabytes in the case of Wikipedia, which is quite a lot. So it's very easy to show that the time complexity for the hierarchical approach is lower than for the flat one. It's, if k is the number of categories, it's log k in one case and k in the other case. But then, what about the space complexity? If the space complexity of the hierarchical one is way higher than the one of the flat one, then this ratio can in fact turn to the disadvantage of the hierarchical approaches. Another challenge when you're doing large-scale classification, and it's a challenge for almost all the big data sets I know of. It's not everything in big data is big. You've got a lot of very, very small objects. And in this case, it means that you've got a lot of categories of boxes which contain very few objects. For example, here, in this data set taken from Wikipedia, with, among 36,000 categories, 15,000 of them have less than 5 documents, and 4,000 of them have just 1 document. So in this case, it would be really difficult to learn something because you have very few information to infer more. Okay, so I will now try and provide some and present some solutions to these different challenges. So first, I want to start with the hierarchical versus flat debate, and I will just give a very short overview in 1 slide, 2 slides maybe, of machine learning, basically. So in machine learning, you assume that you have a system, okay, which from some input provides some output. So in our case, the system is a set of humans, and they have taken some documents, and they have provided one or several categories. Okay? And the goal of machine learning is to, from an observation of some of these x's and y's, is to be able to learn a function from a set of functions that will be able to map the input to some output. And of course, you want the output that you provide to be as small as possible. So basically, the observations that you have is called the training set. Then the class of functions we are considering here are linear classifiers in feature spaces, possibly feature spaces, sorry. And linear classifiers are really the choice usually made in large-scale taxonomies because of time speed problems. Then you've got the decision functions, that is simply you assign a document to the category that has the highest score. And then what you can do is to compute the empirical error. That is just the number of mistakes your function is doing on your training data. Okay? But this is not exactly what you want to optimize when you want to select a function from a set of functions. What you want to optimize is what we call the generalization error. That is the error that your model, your system will make on all the possible examples that you are going to see in the future. Okay? The problem is this cannot be computed in most cases because we don't know the joint probability of x and y. So people have developed several theoretical frameworks to find a way around that and find good approaches to estimate models. And one of the most known framework is the one around Rademacher complexity based on concentration inequality. So basically what you do is you just try to bound the generalization error, the one you are interested in, with a term involving the empirical error, a term involving the complexity of the function that is used, and just a term that is related to the quality of the approximation you want to have and the size of the data that you can observe. So basically, if you now from that, what you can say is if you want to minimize that, so basically we'll try to minimize these 2 terms. So there is a mistake here to be small f. And what we did is just, okay, starting from that, we developed a framework for hierarchical classification that encompasses the flat classification as a special case, and we developed some analysis and we obtained these bounds here. So here is the generalization error for hierarchical classification. This is the empirical error, and this is the Rademacher complexity term. And this is just a term that says TV is the number of sisters, of daughters of node V. So basically, what you do is that you compute at each level, for each node, you compute the square of the x number of sisters, you sum of daughters. So you sum that over all the nodes, and you've got a complexity term for your method. It turns out that this term is lower when you have very deep hierarchies. That is, if you have just a flat classification system, just have one node, okay, and all the leaves below it. So the number of daughters is very large, and this term is very high. So the interpretation is of this bound, this previous bound, is that is the following: the complexity term, as I said, privileges hierarchical structures, but at the same time, this term, which is linked to the empirical error, privileges in fact flat classification. Simply because when you're doing hierarchical classification, if you make a mistake at one point, then you're not. It's not easy to recover the mistake, and you can even propagate the mistake further down the hierarchy. So usually it's easier, especially when the classes are well balanced, to have a smaller term here when you're dealing with flat classification. So this bound exhibits a trade-off between empirical error and complexity terms. So this is just an illustration of these two terms on some data sets. So here, for example, I just want to focus on the last two columns. The complexity ratio, it's the complexity ratio between the hierarchical and flat methods. It's the empirical error ratio between the hierarchical and flat methods. And you see here, for example, these two ratios, they are rather small, okay, compared, for example, to these ones. Meaning that it's very likely that the hierarchical methods will outperform the flat ones on this case, and that the hierarchical method will, compared to the flat one, will be better on this collection than on this one. Okay? And if you indeed deploy classifiers according to a flat strategy or hierarchical strategy, you end up with these results showing that in all these collections, the hierarchical approach is better, and on the last one, the flat approach is better, okay, which is in line with the bound provided. Okay. Just an interlude here. It's also possible, and this is something that was published in CKDD. It's also possible to show that for power-law distributed category systems, and this includes all textual category systems, the space complexity of the hierarchical approaches is lower than the one of the flat approaches. So basically, what it means is that if you want to be fast to hierarchical classification, it will be faster than flat classification. This is not necessarily true for image categories. So basically, because of these results, it suggests, and the fact that the hierarchical can be better than the flat one, it suggests that one can also try to do taxonomy adaptation by simplifying the taxonomy, so basically by removing some nodes of the taxonomy in order to end up with a simplified hierarchy that would still be fast, and that could be better in terms of accuracy, especially when the flat approach is better than the hierarchical one. So we can do that from the bound above. So the bound above was mainly a theoretical results. It explains some of the results reported in the literature, but it's very difficult to design an algorithm directly from it. However, it provides ingredients from which you can try to define features for nodes and then learn a meta classifier that we can use. This node should be removed or not. And that's what we did. I don't want to spend too much time on this, but basically that's what we did. Just design a meta classifier on some taxonomies that will learn whether a node should be removed or not. Then you apply this meta classifier to other taxonomies and you simplify the taxonomy. And here are some results we obtained. So this is a fully flat approach. Here it's an approach where you randomly remove some nodes in the taxonomy. And this is the fully hierarchical approach. And the last two lines, these are the lines obtained with our training strategy. And what you can see is that even in the case of the IPC, we were able to where the flat one was better than the hierarchical one. Yeah. In this case, we are able to have better performance than the flat one, and we are definitely faster. So pruning the taxonomy improves classification and leads to still fast classifiers better than the flat ones, faster than the flat ones. So what I've presented you so far is that our developments aiming at addressing two of the challenges I mentioned before. The first challenge was which approach to use, flat hierarchical, which hierarchy. And so we have presented presented a theoretical explanation of that and a way to do taxonomy adaptation. And then we have just mentioned a result we obtained showing that hierarchical classification is really fast. The third challenge I would like to spend some time on is dealing with rare categories. So this picture illustrates the fact that it's very difficult for any learning method to be accurate on rare categories. So here on this axis, you've got the rank of the some categories in the category system, and the category rank first is the category that contains the most documents, it's the most populated one. Okay? And here you have categories with very few documents. Okay? And here you've got the number of documents in each category. So this is a log scale. And in black is the true numbers of documents per category. And in white, it's the number of documents assigned to this category by a learned model. So what you can see here is that there is a huge difference on the top categories. Okay? Meaning that the learned system will put more documents in these popular categories than it should. But at the same time, of course, here, for example, we see that the learned system doesn't put enough documents into some categories. And even some categories are out of 1,100 classes here, only 570 are discovered. That is, classes with very few documents are not even considered by the classifier. Okay? So the question we had was, can one quantify the difference in the distribution induced by a classifier and the true distribution of the test set? And that can this be related to an upper bound so that we can devise an algorithm in order to deal with these rare categories. And we ended up with this simple upper bound. So this quantity is the number of documents assigned to category L by the classifier. So it's basically the white elements, the white dots. And this quantity is, in a way, an estimate of the number of documents that should be in this category. And this estimate is based on the probability, on the class probability derived from the training set. Okay? So it means that we rely on the assumption that the training data and test data have the same distribution. So basically, if we want an estimate of the real number of documents in a particular category on a test set, then we can estimate it by this product, which is just the class distribution probability of the class on the training set. So this is just an estimation of the black dots, okay? And we can show that the accuracy of a classifier is bounded by that. And then what we can do is say, okay, we can try to design a classifier so that we have a better upper bound for this accuracy. Okay? And this classifier, we did that through this method, which is simply you learn your classifier in a standard way, and then when you categorize documents, if there are two categories that are close to each other for a certain test document, and they involve, and one is rare and one is rare and the other is really popular, then there is a hint that you are that your system is biased towards the highly populated document category. So what you do in this case is just sample some examples from these two categories very quickly, relearn several classifiers, do that several times, and then take a majority vote on this particular example. So it's a bit slower than the standard approach at prediction time, but then it allows you to have a better estimation of what's happening on these rare categories. And if we do that on this example, we obtain significant improvements on both the micro and macro measures, which are two standard measures. This one really tries to assess what's happening on rare categories, and this is from a single SVM, and this one the state-of-the-art method on multi-class SVM so far, and you see that you can gain and you can have significant improvements on this method. And more important, maybe, is that now we move from 570 to 650 discovered categories in the test. Okay, so to conclude, I just wanted to give you an idea of the problems that are encountered when we do classification in web scale taxonomies, when we are dealing with a lot of classes. Standard machine learning methods, they focus on few classes, I would say, but because of the availability of web scale taxonomies, there was a need to deploy to better understand what's happening in this large scale category systems. And what I showed you is a theoretical explanation of the performance of various methods, a method to do taxonomy adaptation. And there definitely are other methods to do that, and this space is, in a way, really poorly investigated at the moment, and several groups are working on that. And then there is definitely a need to deal with rare categories in such big data problems. Thank you very much.
Thank you. So thank you, Eric, for this mention in the hierarchical classification issue. Are there any questions from our audience? So I have several actually, but I will not spare much time. I will start with one. So this hierarchical classification deals with some kind of fixed hierarchy that we use all the time. Is there any, I mean, according to your experiences, are there any chances that, first of all, make this tree some kind of a graph, which means that categories might be related to more than one parent?
So yes, the answer to that is yes. And in fact, you can use more or less the same techniques that I mentioned for that. There are also approaches that try to reformulate the categorization problem when the number of categories evolve over time, when the categories evolve over time. So there have been some solutions proposed to that. It's a bit transversal to what some proposed, but yes, there are even some methods that take that as input, but you don't want to deploy them on such scale.
You know, on the intuitive side, do you think that these hierarchies could be learned from the source data? A little bit with natural language processing that can, for instance, we know that in Google there is this knowledge graph project that tries to.
Yeah. So yes,
what could be the role of hierarchical classification?
So there have been many studies on that in the past, and in a way that there are three main scenarios. When you start with just the objects, just the documents, and you try to infer the structure, and people use just to that. There is a scenario where what you do is you interact with an expert in the process of building the hierarchy. And this is interesting because, in a way, you can also each time you can ask the expert to decide on merging two nodes or on splitting nodes and things like that. And you can also do that with the kind of bounds I mentioned in mind, so that you have a taxonomy that supports the experts and the classification purposes. And then there is a third scenario where you start with some categories already, say the leaves, and then you try to infer the hierarchy, either automatically or with the expert, but starting with already existing categories.
Thank you very much. Again, thank you. And let's welcome our next speaker. It is Manuel Gomez Rodriguez, who is a researcher at Max Planck, a leader of a research group actually in the Max Planck Institute for Software Systems in Saarbrücken, Germany. Previously, he was a postdoctoral fellow and research scientist at the MPI, which is the other institute in Saarbrücken. He has received his PhD from Stanford University, and his interests include machine learning in networks, like network inference, temporal dynamics, convex and submodular optimization, brain-machine interfaces. He has also achieved Best Paper Award in KDD 2010 and LIX 2013. So we are very glad that Manuel was able to accept our invitation, and the floor is yours.
Yeah, thanks for the kind intro, and I'm very happy to be here. Actually, back from the days in Stanford, I was always impressed that all French graduate students, they seem to come from Polytechnique. So it seems the only school, but I guess was a bias sample, but I believe you are in a good place here. So today I would like to present this thing. I mean, to talk about social activity, and in particular, how to try to control or to kind of influence the social activity. And this is kind of a project that I would like first to put in context, but will be mainly a project. And it's joint work with some collaborators in Georgia Tech and also some graduate student in Spain, Carlos III. So let's see a bit what is the big picture now is that we are surrounded by networks. You can think, I don't know, many of you now next to me, there was one of the organizers posting that there is this streaming in Facebook, or some people maybe writing something in Twitter about an event. So everybody is actually, almost everybody is using social networks of some kind to kind of interact with people they know or simply with like acquaintances. You can think also in more traditional World Wide Web, no? That I would say almost everybody in the Occidental world use to find information or to check news or things like that. Also information networks, before some of the speakers was talking about Wikipedia, or even they talked before mine about taxonomies of entities. So you can go to Wikipedia and to browse through this information network. That here the different articles would be connected by links, so you can navigate through this information network. And these would be networks that you use somehow, but that somehow you're in a computer. So it's not that you are moving through the network physically, but you can think here in Paris, when you take the metro, you go through the network of the metro, and it's yourself the one moving from node to node. That would be the station. No? And you can think also of many examples, I don't know, like protein interaction networks, electrical networks, things like that. No? And as maybe you guys already from the first talk in the morning, the keynote, that there was tons of work about the structure of these networks. And there are tons of work about the properties. I think in the talk was talking already about Newman, about communities. You can think of things that they got very mainstream, like these 6 degrees of separation. You take 2 people in the well, they are connected by 6 hubs. No? And they study many people properties, and after they propose models. No? That the idea is to create synthetic networks that somehow they try to mimic these real networks, and in particular to fulfill some of these properties. No? But as you can see in some of the references, I mean, you can go back to 60s, 70s, and I mean, the review that the first speaker was talking about has over 2,000 citations. So give you an idea, okay, there are tons of people that has worked on this topic. No? But what I'm going to talk today about is more about the processes or the activity that take place over this network. And the thing I find exciting that this is much less studied. And in part it's because it was difficult to actually have traces of this activity. Right? So to talk about that, it's good to make a bit of an I find useful to make this distinction that you can think, okay, you have some structural connectivity, that let's focus a bit in social networks. So you go to there to your profile, and you can see the number of friends that you have, that could be the connections, or in general, the number of users that use the social network, something that can be changing, but somehow is like, doesn't tell you anything about the activity itself. But when you think in activity, you could think on what I call here like functional connectivity. No? That would be, okay, if you go to Facebook, nobody of your friends talk about anything, you wouldn't come back that frequently because there is nothing to check out. So in this case would be, okay, how many of these users are active? Or how many of these connections are active? Maybe you have 500 friends, but I don't think anybody talks to the 500 people. You talk to some of them, and depending on the time, to one or others. No? And this functional connectivity is what gives you, okay, there are some good things, not this engagement I was talking about. If it is active, you are going to come back to the site because somehow you want to check out if something was there. Also, like in Facebook now, they managed to somehow get some money from advertisement. In part is because the user is active, so they know how the user is, so they can target the user. And also, like for viral marketing in general, if you are an advertiser, you would like some active network. Otherwise, if nobody goes there, really nobody is going to be engaged. But at the same time, you could say, okay, there are also bad things of that. No? Like if there is a rumor, and the functional connectivity is very strong, then the rumor spreads very quickly. Like I don't know if you remember some Twitter accounts that got hacked, and somehow there is some bombing, and suddenly the stock market goes down because there was no time. It was too fast. No? And at the same time, we got also some work studying information overload. That you could say, okay, you are overloaded by information. Here, maybe when you go to some research field, you check out the papers, you start to get a bit anxious that there are so many people working, so it's impossible to read everything. And to give you an idea, I mean, I didn't actually know there was a speaker from Google, so I don't want to piss him off either, but what happened when you don't have functional activity, I guess is one of the problems you have in Google+. You have a huge graph, it's massive, but it is what they call here ghost town. No? Nobody's actually using it. I mean, the friends I have that use it are mainly Google employees, so it's something we would like to fix. So why we can actually focus on this activity is because right now we have otherwise. So you can keep track of many of these activities. I mean, here are different examples of messages. So you can see not only who writes the message and when writes the message or the information, but you can see also the number of retweets, or you can see the number of favorites or the comments, and you can actually hash all this timestamp data. It's not only that you know it happened, you know when it happened. And the nice thing of that is that, okay, this availability of these digital traces can somehow give some hope of saying, okay, to have data-driven methods to try to either fit this activity to create models or to even have some optimization problem. And to give you an idea of the context of the type of work I try to do, is that I try to do partly data analysis, also like probabilistic models, and also learning methods. No? And it's to understand, to kind of predict or control this activity. No? And mainly is over social networks and information networks. And the thing that was already mentioned before this morning is that it's very interdisciplinary. They were talking about big data, but in the case of networks, for example, and this activity over networks, you have to know about many different things. To be able to do that analysis, you have to be able to crawl the data, or you have to be able to process these large quantities of data. And moreover, it's like very recent. So it's not that you go there with some new idea and somebody tells you this was already done 20 years ago. I mean, it may still happen, but it is easier to make some impact. Not that is what makes me very excited about it. Yeah. So what is common about this idea of activity over networks, if you think more in like engineering or mathematical point of view, is that you have some stochastic process that is happening over some large network. And here the strategy would be, okay, first you want to have some kind of realistic model of activity so that you can test different scenarios, and you want to fit this model using actual traces, like real data. And finally, that is mainly this talk, is going to be about optimizing some quantity. But in this case, it's going to be try to actually steer or influence this social activity. So as I said, by steering using activity in a social network, we are meaning that, I mean, why we would like to do that is if you read the news, they are talking all the time about engagement. This example of Google Plus would be the same idea, no? That you don't only want to have a social network with a lot of users and a lot of connections, but you want people to actually use this social network to post information. No? And it seems kind of a goal that is pretty ambitious to say, okay, I'm going to do some magic here and tell you, okay, that way everybody starts to talk about. So I'm going to give you a bit of intuition that I will use through the talk later. No? So it's to distinguish these two types of activity. So the first one on the left would be the exogenous activity. So for example, now the person next to me was posting that there is a YouTube video. He decided to do it by himself. It's not that nobody actually was not replying to something. And on the right would be the endogenous activity. One of his friends actually likes this comment or comment on this comment. So it's an action that is triggered by other. It's a response, no? So if we see some example here visually, we would say, oops, I'm not sure why it's not showing that. Okay. Okay, I'm not sure why.
is okay. Sorry. 1 second. No, I have Wi-Fi. I'm not sure why exactly happened that the things disappeared. But I have a copy of the movement. Yeah, the presentation, but I'm not sure why they disappear the images. But, okay, here they are. Okay, yeah, sorry about that.
Yeah. So let's see an example that is actually visual that you can see here. So there was like somebody that maybe some of you know, like was the actor of 2 Men and a Half that somehow Charlie Sheen. They at some point they fired him, and at that point decided needed an intern. No, so put like some tweet in Twitter that was asking, okay, I'm looking for an intern. But I mean, I guess it's different type of interns that the interested students would try to look here. So this was some exogenous message. So if you see here, now suddenly people got very interested because he's famous. So they started to retweet it. They started to say, okay, this is my favorite message. And this triggered actually like a discussion about it. So the exogenous activity was the original tweet that he decided out of nowhere, I want an intern. And afterwards, we started to create a lot of activity that was simply as a response to this activity. So the idea is going to be, okay, this is the type of activity that we are going to try to control in a way that is optimal so that we can trigger a lot of endogenous activity so that there are responses. And to do that, we want to also choose like a few users. It's not that we are going to try to make the network active by paying everybody to post things, because otherwise, I mean, we would run out of budget. And at the same time, maybe we don't want only in focusing on Charlie Sheen, like, okay, maybe some people don't care about him. No? So maybe you want to actually pay him a little for a bit of activity, so that creates some of this endogenous activity. But since we are more like in the web community, maybe we would like, okay, maybe James Bernard-Lee is able to publish things that are more interesting, and then you somehow pay a bit to him. But at the same time, maybe you say, oh, well, the difference in followers is like 20, yeah, like 200 times or 100 times. So maybe you want to say, okay, I take Elon Musk, that somehow is more up to date and has more followers, and I pay him a bit more. So here you would distinguish again, okay, what you pay for is for some exogenous activity. And what you are hoping is to pay the right people so that the endogenous activity is actually increasing. And here the idea is that you are not paying them for a message in particular. You pay for a rate to say, okay, publish like 3 tweets per month, but publish whatever interests you, but use our service. So in that sense, we try to make it more realistic. It's not that you want to spam the people so that they get angry that everybody starts to talk about this internship of Charlie Sheen. It's that they can choose what they talk about. But simply it's about the activity itself. So how are we going to try to do that? Is that initially we introduce a model that to show that it's realistic is not really the main goal. We have some papers that actually show, okay, it's the real data. After that, this model, we will see how we actually can catch this problem of activity saving. And in the end, you will see some real data experiments that we try to do somehow like a simulated intervention. It's not that we started to pay users in Facebook or in Twitter to spread things. That would be even later, but we didn't have the budget to do that. So let's start with some very simple model. So here, what you have in the figure is like different Twitter users, no? And for every user, you can have like a counting process that basically tells you every time that they publish a tweet, this counter increases. So for every user, you can do this. There is no assumption. I mean, you take simply the users and you start to count the tweets that they are publishing. And here the idea would be, okay, if you focus in a very, very small time, somehow the increment in this counter will be proportional to some intensity. And here the key point is that we want this intensity to pass memory so that you know what happened in the past, and also to be time-bound. So the idea is that, okay, if you take this example, this user in this part, was only like, in this time period, it was publishing like 2 tweets per hour. But you go a bit further, maybe there is a burst. So suddenly you have, okay, there is 3 tweets per hour. So we wanted to make it time variant and to say, okay, it has memory. And now once we have this, is how this relates to this exogenous, endogenous activity I was talking about. So for the full activity of somebody, like of every user, you could say, okay, there is some activity that is exogenous, is what they decide to post. And there is some other one that is like simply replies to things. And again, to see it more clearly, we put an example that is kind of up to date. No, it turns out this robot that now is without battery, but it has a Twitter account and was publishing, okay, I arrived to the asteroid zone and doing some experiments and so on. So it was publishing some tweets per hour. And you could say, okay, it has tons of things to say more than to retweet from somebody. No? So if you actually compute for this day, the rate, you would see, okay, most of the rate, like almost everything, was simply exogenous. The guy was telling you how it's doing. But at the same time, at some point, decided also to retweet something from the base station that was on Earth. And okay, there's going to be a video of somebody explaining how the robot is doing. So here would be this, he decides himself to do it. This is as a response to another user that is following. So how do we do this thing of how do we model this endogenous activity, the responses, no? We try to make it very general, to say, to give you an idea, every time that an event of a friend happens, that, for instance, here we have the base station, would be, okay, there is a spike in the rate, in the sense that at that point, realistically could happen, the person replies. But as long as there is no message, there is no rate. So every time that there is a message of one of the friends, we have one of these spikes. And in some of them decides at some point to actually, okay, to publish a message. No? And you could say, okay, what is the shape of this spike? It's something that you could try to fit to the data. Okay, it's like exponential decay or whatever shape. And also the influence of the neighbor. No? Maybe you follow many people, you never retweet one of them. So this weight would be 0. It's like, okay, whatever he does, you are not going to respond. And then to give you even more an idea of this thing of the spike, no, is that to model somehow the lifetime of a message. To take a user with a lot of that follows a lot of people, the feed will be very fast. If you take a user like me that I follow 60 people, it's very slow. So whatever tweet is there is going to remain there for a while. So the lifetime is somehow became slower. So as I said, it's not the main message of this talk to try to model, to fit this model. But to give you an intuition of how we do that is that we can map actually the rates to some likelihood of event. And afterwards, we simply say, okay, we apply maximum likelihood and we fit the parameters of the model. And trust me that we validate it using real data and saying training set, test set, and so on, and to check that actually the model is working. And we use actually an exponential decay for the memory. So this is another story. And even there is some French mathematicians, Malat is called, that maybe you know, that has some work in how to actually estimate this thing non-parametrically, even, not assuming like an exponential, how to do it for simplicity. So the better you manage to fit the model, if you take the more general model, the better, but the method still works. It doesn't matter what you choose as A or B. So now that we have the model, no, I was talking about activity and saying, what does it mean mathematically? What we try to say is that we try to have some average activity at a given time that we want. And this average activity somehow is over the all possible histories. That is something stochastic. We cannot fix the history. And basically to do that, now the question is, okay, but if we want to simply like to fix the exogenous intensity to manage to arrive to something we want here, how do they relate? I mean, doesn't seem trivial. It's okay, here you are fixing only the exogenous, but the endogenous are different, like these are like not three, but it's a structure, a branching process that is stochastic. So to give you first, like the answer directly, so that you don't think it's something very complicated, is that actually they relate linearly to a convolution. This would be the exogenous activity. Here there is a time-varying matrix. If you convolve these two things, you manage to get the average intensity in the overall network. That would be by average intensity, I mean exogenous plus endogenous. And the idea is this matrix depends on this the memory and this influence matrix. No? And I'm not going to go into all the details, but if I write these things a bit magic, so I'm going to try to give you the intuition of how do we get that matrix and why is the convolution. So imagine you have a social network, simply. And now this graph seems a bit involved at the same time for the social activity, but I will try to explain it. No? So you have some events that are exogenous. Like here, like the user one, that would be this one, is like talking about something exogenously besides. And this trigger endogenous event. It's like this guy is retweeting him, and this is retweeting the retweet, and so on. So you could think, okay, you can build such a tree. No? And here is one of the key insights that you can start to say, okay, what is the counter of say exogenous? What's the counter of retweets, like the first level? What is the counter of second level, and so on until infinity? No? So if we represent it in this way again, you see that in the same way we can start to define rates for every of the levels. Not only like exogenous and endogenous, but for every level you have a rate. And here is the key thing, no? That when we take the average, it's the average over the histories. But the exogenous activity doesn't depend on the history. It's something you decide to do without taking into account the previous events. So when you take the average, it's actually simply they are equal. So now what you do is, like for every level, you can show that you can somehow backtrack until the exogenous one. And the details of this is using like a convolution of kernels, and is not very important for the talk. It's simply this idea that you are kind of backtracking level after level. So once, and finally the last detail now is that in the case this, you can do it generally for any kernel. But somehow for the exponential kernel, it's easy to compute that quantity. So you can actually solve the sum of all these convolutions. You can compute it analytically. And this is like directly an expression that depends on the influence, like this, those weights of the influence of the people and the decay of the kernel. But again, this is convenient to compute it analytically, but you could do it for any kernel if you do it numerically. And once you have that, okay, we can actually create it. Yeah.
Do you do assumptions on the structure? For instance, I got the impression that you assume a tree of retweets. If it is not a tree, but it is a graph, does it change anything in your design?
Well, is the temporal structure. You assume you cannot copy the past.
Okay.
So they give you a die. And here, like for the remainder, okay, assume we don't do time varying intervention. It's like, okay, we pay for a rate that is constant to somebody, like 3 tweets per day or whatever. But we could do it for time varying things, but for the validation, otherwise it's a mess. So once we have that, now, okay, how does it, how do you look together these two parts? No, since we didn't know how to compute that, now basically every time we have an activity shaping problem, could be, okay, we have a goal that would be, for example, maximizing the average rate of everybody, or could be something else. But this is very flexible, and then you simply have the expression, and you have some budget constraints that you can only spend some budget. So a few examples to give you an idea is, for example, if you want to maximize the activity of all the users in the network, you also have to take into account that the users have a limit. It's not because you pay somebody is going to tweet 1,000 times. So accounting for that limit, because of that, you see this minimum that is only for that. So this would be, okay, we are trying to actually fix this thing of, okay, we want to increase the engagement in general. But at the same time, you can end up like Zynga, no? That Zynga is this online gaming company, but they have this problem that only 1% of the players were actually like profitable, let's say. So in this case, you could say, well, I want to maximize the less active users so that everybody somehow keeps some activity, no? Again, this thing we can solve it. It's like a convex problem. And at the end, like the more challenging thing would be, okay, you want to actually have this particular rate for this particular user and per group, so whatever you like. So you would say, okay, you try to simply fit the average rate to whatever you like. In all these cases, it's a convex program, and there is no time in talk, but we develop some numerical methods or reduce some numerical methods that are especially fit for this problem. But I just skip it. I mean, you can talk to me if you want to know exactly how we solve the convex problems or how we compute this matrix. That is not easy to do. But now to kind of conclude a bit with the experiments, no? The way that we did it is like we have some Twitter data set, but I mean, we say the method is scalable, but to validate it, we take all events of 3 years of Twitter that we have. It was kind of complicated. So what we did is we only took the tweets that they contain a shortening, a URL shortening. And that is the data we actually use. That still is like a huge amount of data. I skip the slide because it's again not to give a lot of details. And one of the characteristics is that this URL shortening, this data set was from 2009. So there were different of these bitly tiny URL. Right now, there is the default service. But in this case, there was several, and they were mostly using Twitter. So you don't expect a reply to happen somewhere else. So after we built like 2 networks of like 2,000 users and 50,000 users, to say over 8 months, no? And we didn't take larger networks because to do like systematic evaluation, otherwise it becomes a bit difficult because we repeat the experiments many times. And we fit the model for different subperiods of this 8-month period. For every of these subperiods, we fit a model and we run many of different activity shaping tasks. And after first we simply check, okay, the theoretical thing we were trying to achieve within simulation with the fitted model from real data is actually true. But after we did this complex held-out evaluation, that offline I can explain to whoever wants to know. But a bit idea is trying to say, okay, that the intervention we would be doing to somehow check would actually have the effect we are looking for. It's a bit complicated to explain now, but if somebody is interested, we can explain. So here are a bit results like for 2,000 users, no? We compare with several baselines. And this is for the maximization. So here you would like to have the data rate. And this is our method. This is some baseline. This is some baselines. So by baselines, we mean things like, okay, you take the nodes with the highest degree or things like that you could expect from trigger interaction. And to give you more like, okay, some numbers that are easier to understand, no? Is that compared to the best baseline, like the second best method, we managed to get like 10% more events. That for this data set of 2,000 means 34,000 more events per month. So that is easier to actually get what we need. We did the same for like when we try to maximize the less active users. And again, we designed some baselines that somehow make sense. And after, if you compare in numbers, no, we say, okay, we managed for the less active user to duplicate this activity. That in this case, because it's the less active, means, okay, we managed these people to produce like 4 more events per month. But again, okay, take into account those people, they were not probably using Twitter. And finally, this thing of saying, okay, when you try to actually fit some particular vector of rates, and this is the error, so the lowest is better. And we compare again with some baselines that we try to design to say, okay, this is something reasonable. Here, I don't have numbers to say, okay, we managed to do 3 tweets more because it's like simply the error, but I have some other plot that gives you some idea. But here, the thing to understand this plot is that we divide the users in like 3 groups, and we try for every group to reach this average level of activity. And what you see in blue is simulations with a fitted model from real data. So as you see, I mean, it's something stochastic, so you cannot expect, okay, it's going to be exactly matching the thing. Otherwise, it will be impossible. But you can distinguish still that you have those levels. So a bit to wrap up, no, I try to give you an idea of a project in particular that, as I said, would be more about control and would be more about learning methods. But there are many other things that you can do, more mathematical, more practical. So there are tons of opportunities for different profiles, and since already the first speaker started with some advertisement, and since, as Mikali says, I'm starting a group, so I'm looking for interns or doctoral students, postdoc, or visitors in general. So if you like this work, or you can check the actual paper in the website, or to check out what I do besides this. And if you are interested, send me an email. Thank you.
Again.
So are there any questions to the talk of Manuel? This is about how to enforce larger activity on, for instance, Twitter, right?
Yeah.
Do you think we can really, let's say, make an effect with these, let's say, targeted tweets that can create endogenous activity? I mean, have you tested only on past, or have you tried that?
No, we tested on past. But I would say yes. But the thing is that would be nice to actually try. But it's another type of I mean, require much more effort to have the method, the observational data, you can test it.
I would assume that the industry would be interested in that.
Yeah. But I mean, it's like, I don't know, when before coming here, I posted something in Twitter with the hashtag data science or whatever, and suddenly I got retweets from people like, they started to follow me somehow and retweet it. So it's like, okay, that there is actually good response every time you see people retweeting things or liking things, stuff like that. So a challenge is that the network is time bound. And actually the retweets, they trigger new connections. So it would be nice to extend this to take into account that the network is changing, but the activity itself.
I see your work as well is somehow related to epidemics, like the SIR, etc. Did you see any synergies between or applications of your work into epidemics?
Is that usually those models, they have like macroscopic data,
Exactly.
and they have some differential equations or some difference equations, and they try to fit the overall global activity, having some qualitative insight and so on. But we try to say, okay, we take the macroscopic data. So in that sense, it's a bit different.
Yes, I think that it's interesting to use this model to check prices on application social media. You want to use because you could create dates actually created by an ad actually. So
yeah.
was also able to
Yeah, definitely.
Okay. So thank you very much once more. And let's move to the next speaker, to the last talk before the lunch. So it is Professor Mark Tomasi, who is a professor in computer science department at Lille Fries University and the leader of the machine learning and information networks team called Magnet at INRIA Lille. He has received his PhD from Lille again, and his research interests are on machine learning, structured prediction for trees, graphs, tree automata, and set constraints. And his talk will be on machine learning for graphs and beyond. The floor is yours, Mark. Thank you very much for being here.
Thank you, Michel. I'm very happy to be here to present the work we conduct, the research we conduct in Lille. Yes, you have heard this word many times now. And you know that Lille is not so far from Paris, only 1 hour and 40 minutes far from Brussels. And if you look at train timetables, you find that Lille is also half an hour far from London. Okay, there is a jet lag. So it's maybe easier to go in Lille than in Saclay. Okay. Okay. I just want to start with a presentation of what we do in Magnet. So this starts with something. Excuse me. Okay. This starts from an observation of this is my okay. An observation of what are the new trends in information systems. You know that today's information systems are very powerful to answer queries, well-known queries on data sets that are constructed in order to answer to those queries. But now, new information systems, they do more. They do anticipation. They want to provide you what you should do in the near future, and what you should do, what you could do. And they are also able to make suggestions and to make recommendations. For instance, I will play accordion this evening. So and they are also able to give you personalized or collaborative answers. And to do that, they are able to do that because they have collected a large amount of data. And this data is now more and more personalized and more social data. But even if these new information systems are starting to do that, there is some room enough to improve the systems, and there is some opportunity for people that do machine learning, because those tasks are very difficult to solve. So because we have complex data, we have heterogeneous data, we have structured data, that is data with many relations, and the semantics, because most of the time there are many text in the data, so the semantics is not very clear. And the tasks for the machine learner is such that the dimensions are very large, input as in, and output as well. And we have only few supervision for this task. And also, as I said from the beginning, what is new also is that this acquisition was not made with a certain application of mind, and we want to be, let's say, to adapt and transform. We should adapt and transform the data in order to solve this task. Okay, so the topics of the group of Magnet is to mine and to learn from these information networks. Okay, so, but I will focus now on what exactly we do. We consider also these information networks and mathematical abstraction of these networks as graphs, and maybe hypergraphs or sign graphs, that is graph with negative weights. And we do machine learning tasks, that is graph modeling and adaptive graph construction, because we want to adapt the representation of the data for the considered task. And we are interested in doing a node and edge labeling or classification in the semi-supervised framework, either online or batch. And we are also interested in making structured prediction and meaningful learnings mainly for natural language processing things. And we're also interested in clustering response trains and beyond graph and homophily. That will be the topic of what I will present now. So I will try to be as fast as possible, because I know this is lunchtime now. Okay. So I will start with some fundamental tasks in machine learning graphs. It is node labeling. It is a fundamental task, because we want to assign a value to every node in the graph. So there are different settings and many settings for that. You can consider the variety by the different value you can assign to the nodes. That is values in the discrete set, finite set, or infinite set, or value which can be mappings or something like that. And you can consider also the case where the graph is static, is fixed, or the graph evolves in time, and so on. And there are many applications of node labeling, because you want, for instance, to predict features in the social network or something like that. And there are also connections with epidemiology and many applications. So a lot of work has been done on this topic. I will focus on a specific task, a simpler task, something that is very long. I will consider the semi-supervised and batch settings. That is, we have a graph which is fixed. I will consider a weighted and unweighted graph, and we will consider that some of the labels are known, and we want to find the labels of the non-labels of the other nodes. So it's what we call the semi-supervised classification, net classification problem. Okay, and the common hypothesis to solve this problem is just to have this homophily or cluster assumption that says that nodes that are close into the graph should have values that are close to. Okay, so to do that, we use a standard approach. We try to find a smooth function of the graph. So if you consider you have red nodes, node labels red and blue on the nodes 1, 2, 3, 6, and we want to find the labels associated with the other nodes. We want to find a smooth function, so we can say that, okay, this one is close to this one, so it should be blue. This one has more red than blue labels, so it should be pink, yeah, and light blue, and etc., etc. And iteratively, you can find a labeling of the graph. And what is used behind is the notion of a gradient, because you for function labeling function of the graph, you will consider on an edge ij the discrete operator that will compute the differences between the values you affect to the labels, and you will add this weight multiplied by this weight, the square root of the weight of the graph. And if you consider the quadratic form of this gradient, you will obtain this expression that is common and which can be written in a matrix way by this formula. And here the term that is a gradient transposed by the gradient is also written delta is called the Laplacian, in this case a normalized Laplacian of the graph. It's more like the divergence of the gradient. And the problem of finding a smooth function on the graph is just to solve this optimization problem that you want to minimize this quantity, the square of this quadratic function f, subject to the non-labels you already have. So the non-labels I have written that like that. So you want to minimize this kind of thing, and you can find analytical solutions for this kind of problem. So this is well known since a long time now. Okay, and it's very easy, but you can see that for a constant function, of course, the gradient is new, and it is, of course, a function that can be the simplest one. But if you have fixed values, you have to take care of that. Okay, but now we know how to do that for graphs. But why I have said beyond graph in my title, because in some situations I want to modelize something that is more than binary relations between items. So, in fact, in a graph, you are representing pairwise relations between items. And now, what the situation when you have pairwise relations between sets of items, and we still want to evaluate individual items also. There are many examples for that. For instance, I will describe an application for multiplayer games. You have the observations of games between teams, and you want to estimate skills of players. And there are also situations where you have a set of machines with clusters, and the clusters are related, but you want to estimate, for instance, CPU loads of the core of the cluster. You have producers and consumers, and you want to find a equilibrium between these two groups of producers and consumers. You have words and documents, and the documents are related, and you have to find a function and So first remark is that the classical graph model is not adapted to do that, and neither the power subgraph, that is the graph of all the subgraphs, the graph for all the subset of nodes, because you cannot infer individual values for the nodes or reasonable nodes. And if you consider hypergraph, it's not adapted neither, because you cannot handle interaction between sets, because an hypergraph is essentially a representation of an array relation only. So we propose a new model. To solve this problem. And this model is called hyperbound graph. And I will do exactly the same thing I have done for graph, but in this case of hyperbound graphs. So what is an hyperbound graph? Okay, so let's start with hypernodes. Hypernodes are just sets of nodes. So there is one hypernode here and another here. And an hyperedge is just a relationship between two hypernodes. And in this relation, we have weighted participation, you can say that, of the nodes, of individual nodes to this hyper relation. Okay? And we will see that we add an equilibrium condition of that form. And this is, we will see that it will be related to the gradient. We will read on that. And an hypernode graph is just a collection of these hyperedges. Okay. So here we have two hyperedges. And okay, and we can see very easily that in the case where hypernodes are just reduced to singleton nodes, we just have the classical definition of graph, in fact. Because of this equilibrium condition, the two weights should be equal here, and so we can do that as a standard edge in the graph. So what is important now is to define what we want to do is to do the same thing that we are doing for graphs. At least I want to be able to find a smooth function of this on this structure, and so we define a normalized gradient by this way. Summing, we have here the nodes on the left part and the nodes on the right part of the hyperedge, and we do exactly the same thing. That is, we weight the left part and we compute the difference with the right part. And as in the case of graph, we have the property that the constant node function has a node gradient in this setting. In my example, for instance, with this weight, we just have the gradient of function f on the hyperedge hp, the blue one, is just 2 times f of 1 and plus 2 times f of 2 minus 1 times f of 3 and minus 3 times f of 4. And you still see that the gradient for this special hyperedge, which is close to the case of the graph, is exactly the same expressions that for graphs. Okay. Now I can define the Laplacian in the same way, and I obtain an object which is interesting because it has some interesting properties. That is, if H is the hypernode graph is in fact a graph, that is, if all hypernodes are just single sets, but this Laplacian is just the Laplacian of the standard graph Laplacian. Okay. This Laplacian is a symmetric positive semi-definite matrix. That is positive to semi-definite operators. So this is interesting. Many applications behind. And we have also this the square root of the smoothness value, which is a semi-norm, that is that legitimates the use of this expression as a smoothness value and a smoothness value for a function. Okay, and by this identity, we still observe that hypernormal graphs are just a generalization, a strict generalization of graphs. We will see that just right now, because the class of hypernormal graph Laplacian is exactly the class of symmetrically positive matrices, such that there are null functions. And so it strictly contains a class of Laplacians, and it is closed also, which is an important property. It is closed also by a convex, linear convex combination. That property is false for graph in general. And there are also a way to compute the graph Laplacian. As usual, we do the difference between the degree matrix, that is a diagonal matrix in which you have the degree of all nodes, and you subtract the adjacency matrix, which is the matrix associated with the weight on the edges. And this is a classical construction of the Laplacian decay of graphs. And if you do that, if you look a little bit into hypernormal graphs, you observe that this class is also the class of this matrices D minus W, but in this case, W can contain negative weights. So the interpretation is that this class of hypernormal graph Laplacians is a class of Laplacians associated with some sine graphs for which this property holds, that is D minus W is a positive semi-definite. And contrary to the case of hypergraphs, we show that we cannot approximate hypernormal graph Laplacians using just graph construction. That is, we have really a difference between hypernormal graphs and graphs. Okay. We can define, because the matrix is positive, we can define kernels as the non-Lagrange rows pseudo inverse of the Laplacian. And this is done also for standard graphs. And here we have additional properties for this class of kernels, because it coincides with the class the class of hypernormal graph Laplacians, because the class is closed as the closure property by epsilon inverse, and also this linear combination, convex linear combination holds. So we can compose those kernels, and we have a conjecture also in the class of oh, this is okay, so the important thing here with this property of linear combination is that you can merge very easily information coming from different graph or graph hypernormal graphs, because you still have the object that corresponds to an hypernormal graph kernel, and you can learn with that. Okay, so I have finished the presentation of the main tool we have introduced. And so, as a summary, I say that I have said that I've introduced hypernode graphs, which are an extension, a proper extension of graphs, and that can represent a binary relationship between sets of nodes. And we have defined a spectral theory for that. We have Laplacians and kernels for this class of graphs. And now we can use that following traditional spectral learning for graphs. We can use this same kind of algorithms to do node labeling and hypernode labeling in that graphs. And we will follow this homophilic assumption. That is, we have an evaluation of the hypernode that will be closed if the hypernodes are closed in the graph. If you look much more deeper on the details, you will show that, and you will see that the homophily property is no more true at the level of individuals. That is because we have some kind of competition between the nodes in the same hypernode, so we don't have that. So we have applied this model to online games, which are usually games with teams of multiple players. So the problem is the following. We have given a set of players and a set of games between two teams of multiple players. And if we observe some outcomes of some match between these teams, we want to estimate a skill function that gives a skill to every player. And this is very important to predict new game results. And it can be used to grid teams and to organize tournaments and something like that, many things in fact. And we cast this problem into a semi-supervised learning problem on that hypernode graph. Okay, so the modeling is very easy. Each game is an hyperhead, and you have 15 A and PV on both sides. And because we have winners and losers, we had on the side of the loser like an additional player in order to have an equilibrium between the two teams. Okay, that's the model. And we have partial information because now we know the result. So this additional now we add is as a value, which is the result of the match. And we try using that to find a smooth function of the hypergraph node, and so that we can associate a value to each player. So in an example, if we have this team 1-2 that moves against this team 3-4-5, we have this additional player on the left side, and okay, and O is the outcome of the game, in fact. And we have the property that it's direct property that the skills are related in that way. That is, the skills of F1 and F2 is lower than F3, F4, F5 if we set F0 to a positive value. Okay, now I consider the problem on the minimization problem of that graph. So if H is the hypernode graph associated with a set of games now, not only one game, but a set of games, we want to minimize this this expression where delta is the Laplacian of the graph, and we add a small regularization term, and we want to constrain the problem so that outcomes are known. Okay, okay, there is an analytical solution to that because we can observe that the regularization term can be represented as another node, in fact, so it's very easy. And we have an analytical solution for this minimization problem. And we compare with the state of the art of games algorithms that are able to predict schemes. So the first one is Elo, which is used for chess competition. It is not related to teams. It is okay, but there are extensions making duels between each member of the teams in order to extend Elo to the case of games with multiple players. And there is another algorithm called TrueSpeed that has been proposed by Arbist and colleagues for online games. And we have the two algorithms we derive from this iconic graph, which are just using the Laplacian, and the other one is using the kernel approach. It's just a kernel approach. So the first one is the one I have described in the previous slides, and the other one is just a kernel approach based on the kernel we have with the Laplacian. So as a result, I can start with single player. So you will say that it's not multiple player games, but because there are players that lose against other ones, we have more than one node on each part of the hyperledges, so we can apply our model in this case also. And in fact, without any few learning, we obtained good results, in fact. Here in the x-axis, axis we have the proportion of games that are used to learn the skills, and they are on the y-axis. And which is interesting is to look at the beginning, because when you know most of the results, it's almost done. So, okay, and in the case of double tennis game, we are red and green, okay? So at the beginning, we are best. We can defeat Elo and TrueSpeed. This is interesting because even Elo is not so good on the single games. And on larger teams, it's more difficult, and we are close to TrueSpeed because yes, we are just a little bit below that. We can defeat TrueSpeed, but maybe it's not significant. Yes, it is significant, but we have statistical for that. But the difference is small. Okay, so I wanted to be fast. I think I have succeeded. Okay, and as a conclusion, I have already said that we have introduced a new tool for the modelization of something that is different from pairwise relationships between sets of nodes. And we have a new skill weighting algorithm almost from scratch and not dedicated to games. And we are working now on online learning in this kind of graphs, and we are studying the notion of cuts and distance and run and walk in this kind of graphs, which are a little bit different. Okay, and open question also in the case of the graph. Okay, I want to thank you, and just recall that, like Manuel, there is a competition now. The open position in Magnet too, so feel free to apply for. Okay, and feel free also to use this platform.
Thank you. So are there any questions on this very interesting talk on hyperbound graphs?
So you have additional modeling power with respect to graphs.
Yeah.
And okay, so there is no free lunch, so you have to pay it when you are not. So I was wondering, why are you paying it? Is it the complexity? What's the time complexity for this kind of composition? There is free lunch.
Size freelance. No, the size of the Laplace matrix is exactly the same, but, because it's a number of nodes. The gradient is a number of hyperrows times. Okay, the difference is it's more like you can interpret that like a specific class of sine graph. It's just a specific class of sine graph where the Laplacian is positive. Which is a, it contains, no, it doesn't contain elements which are not.
Sorry, yes. Is there about implementation?
Yeah.
How can we compare true scheme and
Yeah. All these experiments have been done in the batch setting. So we have fixed, let's say, for these values, 30% of the total set to learn a skill rating problem function. Okay, and we use the rest to predict the games. Okay, and we do exactly the same for LO. Okay, but LO, yes, it can do that in an online fashion. It is not the case for us at the moment, but soon.
Any other questions? So if not, thank you very much, Mark. And I think it is lunchtime. The lunch is served outside. It is buffet. You're welcome to join. We will be back in about an hour from now, or a bit less, or a bit more.